Assalamualaikum.
Waalaikumsalam. Aduh, kok nggak kedengar? Aku jadi khawatir ini. Assalamualaikum. Kedengeran nggak?
Waalaikumsalam, kedengaran Bu.
Alhamdulillah. Saya khawatir aja soalnya suka lemot internetku. Nuhun.
Devita. Ladies and gentlemen, may I have your attention, please? Our algebra seminar is about to begin. During the seminar, we kindly ask your cooperation to turn your microphone off for the sake of conduciveness of the event. If possible, please turn on your camera together with the virtual background we have provided. Thank you.
Assalamualaikum, Prof. Erfanian. Nice to have you here.
Assalamualaikum, Prof. Kuchi. How are you? Good morning. Nice to meet you.
Yeah, nice to meet you. Very early morning, yeah, in your place.
Yes, it's about 7:30 in the morning.
Oh, 7:30. Good to have you here.
So I think the last time was in 6 big TC, right? In
Yeah,
virtual last year.
Yeah.
So how's the situation of COVID-19 in Indonesia? Here it is so bad. So
Yeah. After the Idul Fitri is getting worse.
yes.
Yeah. But now it's I think going better. Yeah. The number of infectious decrease, starting decrease.
Yes. Unfortunately.
Okay, hello everyone. It is nice to have all you here. And then welcome to Professor Ahmad Erfanian as our honorable speaker today. Good morning, Professor Ahmad. Assalamualaikum.
Good morning, everybody. Assalamu alaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. And also welcome to Professor Puji as the head of Algebra Research Group ITB. Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh. Sorry, I was kicked out.
Oh, okay, Bu. It's okay. Okay, ladies and gentlemen, the opening ceremony is about to begin, but we need to wait the Dean of Faculty of Mathematics and Natural Sciences, so please wait for a moment. And again, we kindly ask your cooperation to turn your microphone off for the sake of the conduciveness of the event. If possible, please turn on your camera together with the virtual background we have provided. Thank you. Please wait for a moment.
Kita nunggu apa, Fit? Pak Dekan ya?
Iya, Bu. Pak Dekan.
Udah diingatkan belum?
Sudah, Ibu.
Pak Wahyu suka lupa itu kan?
Sudah oke.
Sudah oke. Udah diingatkan lagi sekarang?
Iya. Tadi oke-nya 10.08 tadi, Bu.
10.08.
Kok dia aku nggak?
Coba aku cek ya.
Assalamualaikum, Pak Wahyu.
Ya.
Udah ada?
Iya, Bu. Sudah.
Waalaikumsalam warahmatullahi wabarakatuh.
Alhamdulillah.
Lupa.
Oke, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi
wabarakatuh.
Good morning, everyone. It is a great pleasure for us to welcome you all to the first day of Algebra Seminar 2021. This event is conducted by Algebra Research Group, Faculty of Mathematics and Natural Sciences, ITB, and I am Devi Fitri Ferdania, will be the moderator of this event. First of all, let me welcome our honorable guest for today. Welcome, Professor Wahyu Srigutomo, as the Dean of the Faculty of Mathematics and Natural Sciences, ITB. Also, welcome Professor Puji Astutiwalyo as the head of the Algebra Research Group, ITB. And then, welcome to all our honorable speakers, Professor Ahmad Erfanian from Ferdowsi University of Mashhad, Iran, and Martianus Frederick Ezerman, PhD from Nanyang Technological University, Singapore. And finally, our warm welcome to all the participants to this algebra seminar. Ladies and gentlemen, this algebra seminar that will be conducted virtually from August 11 until August 12 is aimed to enrich our knowledge in algebra, especially in the field of group theory and graph theory, and also to expand the research network between researchers from all over the world. The speakers will deliver a series of 3 lectures for each topic, and today, for day 1, the topic goes beyond some relations between groups, probability, graphs, and matrices. This first topic will be delivered by Professor Ahmad Erfanian and is divided into 3 subtopics. For the session 1, probability and groups, and then session 2, graphs, probability, and groups, and the last one, session 3, matrices, graphs, probability, and groups. And then for the second day, the topic goes beyond locally recoverable codes and quantum codes from metacircular graphs, and this second topic will be delivered by Martianus Frederick Ezerman, PhD, and also is divided into 3 subtopics. For the session 1, introduction to concepts and tools, and then session 2, locally recoverable codes, and the last one, quantum codes from metacircular graphs. The agenda of day 1 are the welcoming speeches, and then 3 sessions of lectures delivered by Professor Ahmad Erfanian from Ferdowsi University of Mashhad, Iran, in which each session is separated by a break. Also, there will be several announcements at the end of day 1. So without any further ado, we would like to invite Professor Puji Astutiwalyo as the head of Algebra Research Group, Faculty of Mathematics and Natural Sciences, ITB, to give her welcoming speech. To Professor Puji, you might take your time.
Thank you, Devi. The Honorable our Dean of Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung, Professor Wahyu Sri Kutomo, the Honorable invited speakers, Professor Ahmad Erfanian from Ferdowsi University of Mashhad, Iran, and also Dr. Martinus Frederick Ezerman from Nanyang Technological University of Singapore, in Singapore. All dear participants, good morning. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
warahmatullahi wabarakatuh.
I'm delighted to welcome all of you to this algebra seminar organized by our Algebra Research Group of Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung. I'm very happy that our research group can organize this algebra seminar with prominent speakers. Although this seminar is held virtually and simply organized, I hope that it will not reduce the meaning and role of this seminar, which is expected to facilitate a meeting among algebra experts with researchers and students to share knowledge, expertise, experience, and to build collaboration. For that, I would like to thank Professor Ahmad Erfanian and Professor Dr. Ezerman for their willingness to spend their valuable times and efforts to share their knowledge, expertise, and experience with us. I hope that all participants can take maximum benefit from this seminar in increasing their knowledge and building networks. I hope this seminar will inspire participants to come up with new research ideas, get ideas for solving research problems that are being pursued, or form or enhance collaborations. Therefore, I hope that this activity will not end in this seminar, but it will be followed by further activities such as new research topics being investigated, or research visit, or research collaboration. In this opportunity, I would like to thank Dr. Kantina Rahmaputri and teams for this well-organized seminar. And before I close my speech, allow me to give a brief introduction about our group, Algebra Research Group of ITB. Our group has 14 members, 10 of them with PhD degree, and one member currently is in her PhD program, and 3 members are still looking for PhD program and PhD scholarship. Our research interests concerning algebra and module theory, such as hereditary, prime, and semi-prime properties. Research in this area, including research in module theory using categorical approach, such as abelian, triangulated, and derived categories. We are also interested in linear algebra and metric theory, topic in this area, including properties, bilinear, and indefinite inner product spaces. Our member also interested in the application of algebraic structure in coding theory, cryptography, and also DNA mutation. And recently, we extend our interest to graph theory as a result of the visit of Professor Erfanian. Thank you for that, Prof. We are also, our member also patient with mathematics teaching. We are also have active YouTubers, Dr. Aliams Bara, yeah, with more than 60,000 subscribers, yeah. And we also have marathon runners, Kantina, yeah, okay. That's a brief introduction of our group. Finally, I would like to close my speech with wishing you all have nice and fruitful seminar. Thank you very much for your attention. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Professor Puji, for your welcoming speech. And then we would like to invite Professor Wahyu Srigutomo as the Dean of the Faculty of Mathematics and Natural Sciences, ITB, to give his welcoming speech and officially open this algebra seminar. To Professor Wahyu, you might take your time.
Thank you very much. Bismillahirrahmanirrahim. Assalamualaikum. May peace be upon all of us. Good morning, everyone. I was just attended and opened another seminar held by the Analysis and Geometry Research Group of our faculty. So now I'm also delighted to open the second seminar held by our Mathematics Society here. And it is clear that the Mathematics Society is very much alive in our faculty. Thank you very much. Dear colleagues, professors, lecturers, researchers, students, participants, ladies and gentlemen, on behalf of the Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung, I would like to express my sincere gratitude and welcome you to the Algebra seminar held on 11th to the 12th August 2021. And it is my hope that this algebra seminar will be able to achieve its objectives in providing an effective forum for academicians, researchers, practitioners, and students as well to advancing knowledge, research, and technology contributed by the Society of the Algebra. And I honorably welcome our invited speakers, and I would like also to express my sincere gratitude to Professor Ahmad Erfanian from FUM Iran, and also to Pak Martianus Frederick Ezerman, Dr. Martianus from NTU Singapore. And I wish you a very productive online seminar here with exciting and encouraging discussion and exchange of knowledge so that together we can anticipate a future of groundbreaking knowledge, research, and technology from the perspective of Algebra Society. Last but not least, I would like also to express my deepest gratitude to the organizing committee from the Algebra Research Group, led by Professor Puji Astuti, and also to the organizing committee, Dr. Gantina and others, and those who have directly and indirectly supported the success of this seminar. And today, I am very honored and glad to officially open this algebra seminar. May God bless us all with good health to make this event a successful and enjoyable one. Thank you, everyone, and please have an enjoyable seminar. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Professor Wahyu, for your welcoming speech. So, as the event has been officially opened, we would like to invite every participant to turn your camera on to capture today's moment and for the first photo session. So, yeah, please don't forget to use the virtual background we have provided. Okay, we will wait for seconds. Operator, are you ready to take the picture?
Okay.
Okay, great. We will take the photo, I think, 8 times, or maybe 5 times.
5.
Okay, 5 times. So let's prepare our base smile. All right, 1, 2, 3. Okay, again. 1, 2, and 3. Okay. Again, operator, again.
Yeah.
Yeah, okay. 1, 2, and 3. Okay. For the 4th times, 1, 2, and 3. You can change your pose.
Okay.
Okay, and the last one. 1, 2, and 3. Cheers. Okay. Yeah, I think it is enough. Thank you so much, everyone. Okay. Yeah. Okay. Before we start the lecture, there are several technical points and rules for our seminar. So, operator, can you share a slide for the technical points and rules? Okay, great. Yeah, these are the technical points and rules. For the first one, participants have to fill in the Google form to record their attendance, and then you can access the pre-seminar material from bit.ly algebra seminar hyphen material, and then this seminar is streamed via YouTube and is being recorded. The detail for the link for the record will be announced later via WhatsApp group. And then every participant has to join the meeting for at least 5 minutes before the session starts. For the sake of conduciveness of the event, every participant has to turn off their microphone except if allowed. If possible, keep your camera on during the sessions and use the provided virtual background. And then every participant has to attend all the sessions and has to ask for permission from the operator if you want to leave the meeting incidentally. And then any questions can be written directly in the chat box or can be asked directly to the speaker by unmuting your microphone after being allowed by the moderator. And the last point, participants' display name should conform to the provided format, institution hyphen full name. So we kindly ask to all participants that haven't changed their display name, please rename it now. Okay, that's all for the technical points and rules for our seminar. Okay, now we are going to the lecture from Professor Ahmad Erfanian about some relations between groups, probability, graphs, and matrices. Professor Ahmad, can you hear me?
Yes, I'm here.
Okay, okay, it's great. First of all, I will share the short CV of Professor Ahmad Erfanian. Okay. Okay, this is the short resume for Professor Ahmad Erfanian from Ferdowsi University of Mashhad, Iran. His evaluation history is 2002 until 2021 at Ferdowsi University of Mashhad, Iran. And these are his research interests: mathematics, especially in group theory and graph theory, and then multidisciplinary physics and astronomy, engineering, and computer science. And his research record is 136 research items with 534 citations. That's very amazing. And these are his most contributed research paper. A bipartite graph associated to elements and cosets of subgroup and a finite group, and then regularity of generalized bicycle graph. And the last one, the matrix Jacobson graphs of field. So that's an amazing record from Professor Ahmad. And I am very excited to hear his lecture now. So yeah, Professor Ahmad has recorded his lecture for avoiding the instability of his internet connection. But don't worry, he is here, stand by with us in this meeting room. So without any more ado, let's prepare your notes and lean your ears. We will commence the first session, Probability and Groups, from Professor Ahmad Erfanian. Okay, I think there is a little problem here.
الرحمن الرحيم. Assalamu alaikum wa rahmatullahi wa barakatuh. In the name of God, the compassionate, the merciful. Bismillah ar-Rahman ar-Rahim. It's my great pleasure to give a series of talk on first of all, I would like to thank Algebraic Research Group in ITB and particularly Prof. Uchi, Prof. Intan, Prof. Editali, and other colleagues in ITB give some relations between some topics in different mathematics. So we will talk about groups, about probability, about graphs and matrices, and then we'll include 3 parts. In the first part this morning, I will talk about probability and groups. And then in the second part, I will add one graph to the probability and groups. So in the second part, I will talk about graphs, probability, and groups. And finally, in the third part, I will combine all together. So I will add one more topic, which is matrices, to graphs, probability, and groups. This is the outline of my talk. Anyway, first of all, I would like to give a classification about mathematical sciences. Of course, this is not the classification for writing a paper, because we have AMS classification, American Mathematical Society. So this is the just unclassic classification which we actually use in our universities and departments. As you know, if we science, applied mathematics, and department of statistics. In each branch of mathematical sciences, we have some branches of these divisions. For example, in pure mathematics, we have some sub-branches like algebra, analysis, geometry, topology, and so on. And similarly, in applied mathematics, we have numerical analysis, differential equations, dynamical systems, operation, research, control and optimization, graph theory, discrete mathematics, and so on. And in statistics, actually, we have descriptive statistics, sources and data, sampling concepts, regression, data science, probability, and so on. Right? Okay, now what I would like to do here, I would like to take algebra from the and in algebra, you know, we have more topics in algebra, groups, modules, and semi-ring, and so on. So from algebra, I would like to take two concepts, groups and matrices from algebra. And in the second division of mathematical sciences in applied mathematics, I would like to take from discrete mathematics the concept of graph, right? And from the statistics is probability. So we will have four concepts: groups, matrices from the first in pure mathematics, graphs from applied mathematics, and probability from statistics. So I'm going to combine all together and give some relations between these four concepts. Anyway, let us start part 1, which is the probability and groups. So we have two concepts, probability and groups. I would like to remind these two concepts very quickly. I know that all of you know about the definition of probability and definition of groups. So what's the meaning of probability? If A is an event, so the probability of having event A is the number of ways that the event A can be happen divided by the total number of outcomes. So that's the probability of having event A, and we usually use the notation P of A for the probability of event A. As an example, so look at dice. We have 6 faces here. So we have 1, 2, 3, 4, 5, and 6 on each face. And if we take A as an event that having number 1 and B if another event having numbers 2 or 5 and C having an odd numbers, right? So the probability of having number 1 is 1 over 6. Why? Because we have 6 faces, so we have 6 on the bottom, and we have only one. Six, so it's one a very easy example of probability. Now, let me move to the group. As I mentioned, group is one of important topic in algebra. Uh, let us just remind the definition of a group. Suppose that G is a non-empty set, and if we have an operation, we may denote it by a star. So a star is an operation from G cross G to G. So a star will correspond any two elements, for example, A and B in G by A star B. So if this operation is this map a star is a function, then we can say that G with this function is a binary operation. So a non-empty set with a function a star we denote by G comma a star is a binary operation. If we have a binary operation G a star, and if we have the associativity property, which means that for all elements A, B, and C in G, if we have A star B and A star C is equal to A star B star C, if we have this property, then we can say that this binary operation G star is a semigroup. If we have another property for the semigroup, if we have an element E, if there exists an element E in G, such that for any arbitrary element X in G, we have X star E is equal to E star X is X, then an element E is called identity elements. So if G star is a semigroup and has identity element, then G star is called a monoid. Now, if X is an element in G, then we can say that X is invertible if there exists an element Y in G such that X star Y is equal to Y star X is equal to identity. So if G star is a monoid, and if every element of G is invertible, then G star is called a group. So as I mentioned, so the G star, the non-empty set with an operation star, is a group if we have four properties. If G star is a binary operation, if we have associativity, and if we have identity element, and if we have this property that every element in G is invertible. So if we have these four properties, then we can say that G star is a group. Now, if we have extra condition, which is the commutativity, what's that? If we have A star B is equal to B star A for all A and B in G, then we can say the group G is an abelian group. Otherwise, well, it's a non-abelian group. Okay, now let me just give some simple examples. Look at the integer numbers with the usual summation. So it's obvious that Zn plus is an abelian group. But if we take the natural number with the addition. So it's not a group because we know it's a semi-group because we have associativity, but there is no identity elements. We don't have zero. Zero is the identity elements. And also we don't have inverse. So if Zn is the set of all integer numbers in modulo n, and plus n is the sum of two integers in modulo n, right? So it's easy to check that Zn and the plus in modulo n is an abelian group. For example, look at Z4. In Z4 we have 4 elements. We have 0 bar, 1 bar, 2 bar, 3 bar, and 2 plus 2 is 0, 2 plus 3 is 1 because it's 5 modulo 4 is 1. 1 plus 2 is 3, 3 plus 3 is 2, and 0 is the identity elements. And also we know that the inverse of 0 bar is 0, the inverse of 1 bar is 3 because 1 plus 3 is 0, the inverse of 2 bar is 2 bar, right, because 2 bar plus 2 bar is 0, the inverse of 3 bar is 1 bar. So Z4 and addition in modulo 4 is a group and also is an abelian group. Now, the example of non-abelian group, we can consider the set of all matrices 2 times 2 matrices with entries in real numbers. And if we take the subset GL to R, which is the set of all 2 times 2 matrices such that the determinant is not 0. So A times D minus B times C is not 0. So that's the set of all 2 times 2 invertible matrices. So it's easy to check that the GL to R with the multiplication of matrices is a group, but this group is not abelian. For example, look at these 2 matrices. Look at here 1, 1, 0, 1. The determinant is 1. 0, 1, 1, 1. The determinant is minus 1. So the multiplication of these 2 elements in GL to R is not commute. So GL to R is a non-abelian group. Okay. Because we are going to discuss about the group probability, matrices, graphs, so it's actually necessary to remind some important groups. So I'm going to introduce, of course, I know that all of you know the these groups, but just very quick and brief description of these groups is important for us. The first group is the symmetric group. So assume that Sn is a set of all function f from the set 1 to until n to again this set 1 to until n such that f is one-to-one function. So we can easily check that this function, right, with a composition of function is a group, because if you take the multiplication, the composition of 2 such functions to one-to-one function, it's again one-to-one function. We have identity, we have associativity, we have identity function as an identity elements, and because f is one-to-one, so we have an inverse. So Sn is a group, and we can say symmetric group, and we denote it by Sn. For example, if we take n is 3, so S3 consists of 6 one-to-one functions from set 1, 2, 3 to 1, 2, 3. Look at here. F1 is the identity function, so we can take 1, 2, 1, 2, 2, 2, 3, 2, 3. F2, we have 1 goes to 2, 2 to 1, 3 fixed. F3, 1, 2, 3, 2 fixed, 3 to 1. F4, 1 to 1, 2, 2, 3, 3, 2, 2. F5 is 1 goes to 2, 2 to 3, 3 to 1. And finally, F6 is 1, 2, 3, 2 to 1, 3 to 2. So we have 6 one-to-one functions, and we can denote these functions by just cycles, right? So F1 is the identity, we can denote it by the E. F2, we will have 1 goes to 2, 2 to 1, 3 fixed, so we can denote it by the cycles of length 2. F3, we may denote it by the cycles 1, 3. F4 is 2, 3. F5 is cycles of length 3. So it's 1 goes to 2, 2 to 3, 3 to 1. And F6 is 1, 2, 3, 3 to 2, 2 to 1. So we have 6 elements in the symmetric group S3. So we have identity E, 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. You know the multiplication of this, every 2 of these elements, every 2 cycles, we can just start from right to left. For example, 1, 2 times 1, 3, we can start by 1 here. So by this cycle, 1 goes to 3, and this one 3 to 3, so 1 goes to 3. Now again, by this cycle, 3 to 1, and this one 1 to 3, so 3 to 2, and that one 2, 2 to 2 to 1, 2 to 1, so we get 1, 3, 2. So that's the multiplication of 2 cycles. Now, as I mentioned, the symmetric group S3 has 6 elements, so it's 3 factorial, because if you take the number of possibilities for having one-to-one function from 1, 2, 3, 1, 2, 3, so if you take 1, we have 3 possibilities for 1, so 1 can go to 1, 2, or 3. So if 1 go, for example, go to 2, for the 2 we have 2 possibilities, and for the 3 we have only 1 possibilities. So the number of cases is 3 times 2 times 1 is 3 factorial. And it's also important to see that the center of S3, the center of group, which is all elements of S3, which commute with all other elements. For S3, the only identity elements can commute with all other elements in S3. So in general, for symmetric group also, it's easy to check that the center of the symmetric group Sn is again identity. Now, it's very elementary property of cycles. You know, every element of Sn we can denote it by a permutation. So every permutation can be product, can be written as a product of cycles of length 2. Cycles of length 2 called transposition. So every element of Sn can be written as a product of some transposition. If the number of this transposition, for example here k, is even, then we can say X is an even permutation. And if K is odd, then we will have odd permutation. Now, if we put all even permutation of Sn in a set, then we can denote An, which is the alternating group. So the set of all even permutation of symmetric group is the alternating group. For example, A3, you can see that we have 3 elements, right? Identity 1, 2, 3, 1, 3, 2. You can see 1, 2 is not even permutation because it's only multiplication of 1 permutation. But 1, 2, 3 or 1, 3, 2, for example, 1, 2, 3 can be written as the multiplication of 2 transposition. 1, 2, 3 is the product of 1, 3, 1, 2. Or 1, 3, 2 is 1, 2, 1, 3. And similarly for A4, we have 12 elements, right? We have identity, we have 8 cycles of length 3 and 3 cycles of the form of multiplication of 2 transposition 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3. So the order of alternating group An is the half of the symmetric group, so it's n factorial over 2. And again, the center of alternating group is trivial. So as I showed here, the order of A3 is 3 factorial over 2 is 3. Order of A4 is 4 factorial over 2 is 12. So this is the second important group. Now let's move to the third one, which is the dihedral group of order 2 times n. This is the presentation of dihedral group of order 2 times n. So dihedral group of order 2 times n can be generated by 2 elements, A and B, right? A to the n is equal B square is identity, so it means that A has order n, B has order 2, and we have this relation BAB is equal to A inverse. It can be easily checked that these 2 n elements are EA, A square, A cube, A to the n minus 1. So we have 10 elements here. And B, AB, A square B, A n minus 1B. So another B, 10 elements. We have 2 n elements of the dihedral group here. So as an example, if take D6, so for n is 3, we have 6 elements, right? So A and B are generated of this 6, we have a cube called b squared is identity and BAB is A inverse. So we have 6 elements, E, A squared, B, AB, and A squared B. Now, if n is 4, for dihedral group of order 8, we have 8 elements. So again, dihedral group of order 8 can be generated by A and B, which A has order 4, B has order 2, and the relation BAB is A inverse. So we have 8 elements, E, A square, A cube, B, AB, A square B, and A cube B. Similarly, for dihedral group of order 10, so for n is 5, again we have 10 elements, you can see here, but it's important to see the center of these groups. For dihedral group of order 6, so the center of this 6 is the identity subgroup, consists only the identity. The center of the dihedral group of order 8 consists of 2 elements, identity and A square, and the center of the dihedral group of order 10 is the identity, consists only the identity. So in general, the center of dihedral group of order 2 times n is trivial subgroup if n is odd and consists of 2 elements, identity and A to the n over 2 if n is even. Now, the next group is quaternion group. Quaternion group consists of 8 elements. We can denote these 8 elements by 1, minus 1, I, minus 1, J, minus J, K, and minus K. So we have the multiplication of these elements by these rules. I times J is equal to K, J times K is equal to I, and K times A is equal to J. So look at here, this, if you take this circle, so we can put I, J, and K by this direction. So I times J is equal to K, J times K is equal to I, and K times I is equal to J, right? And we have I square is equal J square is equal K square is minus 1. So you can see that A to the 4 is 1. Similarly, J and K also to the 4 is 1. So A, J, and K has order 4. And for example, minus I times minus J is equal to IJ is equal to K. So order of quaternion group is 8. So you can see the order of elements here. We have 8 elements, or 1 is the identity, so the order is 1. Minus 1 has order 2 because minus 1 times minus 1 is 2. I, minus I, J, minus J, K, and minus K, and all these elements actually have order 4. And the center of quaternion group is the set of 1 and minus 1, so it consists of 2 elements. Okay. Now this was very quick reminding of some important groups. We have many groups, which of course they are important, but the importance of one is 4. Maybe that one is enough to use in this series of lectures. Now, I'm going to start the main topic of part 1 of this lecture, which is some relations between group and probability. So it's important for us to combine group and probability. The theory of group and probability is called probability group theory. It's usual for us when we are talking about a property in a group, so we can say that the group has this property or has not. So we can take only 2 cases. For example, if we take the property of commutativity, so we can say that the group is commutative or is not commutative. So commutative means all elements are commute, but not commutative means that at least we have 2 elements which are not commute. So it means that if we have non-abelian group with only having 2 non-commuting elements is not commutative, is not abelian. And if we have many pair of elements which are not commute, and again is not abelian, so it's not interesting to put all non-abelian groups in one class. So that's the idea of defining probability in group theory. In this part of my lecture, I would like to introduce some probabilities, some important probabilities in group theory. Some of them they defined previously, but I will mention about some new probabilities, and also you can try to define some probabilities in group. Okay, the first probability which I would like to mention here is the commutativity degree of a group. What's the meaning of commutativity degree? First of all, I should note that because we are talking about the probability, so we can divide by the order of G, sometimes order of G squared. So we always assume that G is a finite group. So in these probabilities, we just assume that the group G is finite. Of course, for some probability, we can extend it for infinite group. So suppose that G is a finite group. The commutativity degree of G, we can denote it by D of G, is defined by this rule, right? So the commutativity of G is the number of pairs X and Y in G, right? In G cross G, such that X and Y commute. So that's the number of commuting pairs of G cross G divided by the number of all cases, all pairs, which is order of G squared. So the commutativity degree is the number of pairs X, Y, which X and Y commute, divided by order of G squared. This is the commutativity degree. It's easy to see that if the group G is abelian, So what's the commutativity degree of an abelian group? If we have an abelian group, so all elements x and y will commute. So the set of commuting pairs of G is the whole number of pairs, which is order of G square. So if G is abelian group, then the commutativity degree is 1. Now, look at the symmetric group, S3. I'm going to find the commutativity degree for the symmetric group. So, as I mentioned before, symmetric group has 6 elements, right? We have identity 1, 2, 1, 3, 2, 3, 1, 2, 3, 1, 3, 2. Now, I am going to find the set of pairs, set of commuting pairs, x and y, such that x and y commute. So, take the first entry of pair xy. So, if x is identity, how many elements commute with identity? So we know that identity will commute with all other elements in S3. So we have E, comma 1, 2, E with 1, 3, 2, 3, 1, 2, 3, 1, 3, 2. So we have 6 pairs here. Now let's start with 1, 2. 1, 2 commute with only 2 elements, with identity and itself, nothing else. So we have 2 more pairs here. For 1, 3, again we have 2 possibilities. 1, 3 can commute with identity and itself. Similarly, 2, 3 can commute with identity and 2, 3. But 1, 2, 3, 1, 2, 3, we have 3 possibilities. 1, 2, 3 can be commute with identity, with itself, and with 1, 3, 2, because 1, 3, 2 is the inverse of 1, 2, 3, and we know that every element with inverse can be commute. So we have 3 possibilities for 1, 2, 3, and similarly 3 possibilities for 1, 3, 2. So 1, 3, 2 with identity, with 1, 3, 2, and with 1, 2, 3. So the total of commuting pairs is 18, and order of S3 squared is 36. So the commutativity degree of S3 is 1 over 2. Now let us give another example for the commutativity degree. Look at dihedral group of order 8. Dihedral group of order 8, as I introduced earlier, so we have 8 elements, right? Now we have to check each elements can commute with how many other elements in the dihedral group. So obviously, if we take identity elements can commute with all 8 elements, right? The element A can commute with identity, with A square, A cube, right? And A square because it's in the center. So A square can commute with all 8 elements. And similarly, you can see all elements here, and you can find the set of all commuting pairs, which are 40 elements, right? We have 40 commuting pairs, and divide by order of dihedral group, which is 8 squared, so 14 over 64 is 5 over 8. So the commutativity degree of dihedral group of order 8 is 5 over 8. So if you compare the commutativity degree of symmetric group S3 and dihedral group of order 8, you can see that the commutativity degree of dihedral group is bigger than the commutativity degree of S3. So it means that dihedral group is close to the abelian, close to be abelian, right? Because it's the probability is 5 over 8. But the symmetric group is a little bit far. So we can just find the commutativity degree for each of group. So for quaternion group of order 8, if we do the same method, we can find that the commutativity degree of quaternion group of order 8 is 5 over 8, is exactly equal to the commutativity degree of dihedral group of order 8. Now, let us just give a list of some examples without any proof, because we don't have enough time to prove these results. I just want to give some ideas about the probability in group theory. So as I mentioned, if the group G is abelian, so the commutativity degree is 1. And conversely, if the commutativity degree is 1, so we should have G is an abelian group. The second result, which is very important, is an upper bound for the commutativity degree of finite non-abelian group. So if G is a finite non-abelian group, then the commutativity degree is at most 5 over 8. So it means that we don't have any non-abelian group with the commutativity degree bigger than 5 over 8. If we have a group with the commutativity degree bigger than 5 over 8, so the group must be abelian. It's interesting to compare the commutativity degree of a group with the subgroup. So the commutativity degree of a group is always less than or equal to the commutativity degree of the subgroup H. So as I mentioned, 5 over 8 is the upper bound for the commutativity degree of finite non-abelian group. But it's interesting to see that when we have the commutativity degree of finite non-abelian group with exactly 5 over 8. So here you can see that the commutativity degree is 5 over 8 if and only if the central factor, so the G over the center, is isomorphic to Z2 cross Z2. This is a non-cyclic group of order 4. If G is a finite non-abelian group and P is the smallest prime number dividing the order of the group G, so we have an upper bound for the commutativity degree of G, which is P squared plus P minus 1 over P cubed. Look at, if you put P is 2, you will get 5 over 8 here. So the number 6 is very, very important, because we can use the tools of probability to prove some important theorem. You know, nilpotent group is one of important topics in group theory. So we can prove that if G is a group with the commutativity degree bigger than half, then we can prove that G is a nilpotent group. So, you know, by very easy tool, just computing some commuting pairs, right? Then we can prove that the group G is nilpotent. You know, if we want to prove the nilpotent property in direct way, we have to find the normal series and then find upper central or lower central series. So we have to do a lot of things to prove the group G is nilpotent. But here you can see that by very easy computation, you can prove that the group G is nilpotent. Okay, so this is a first probability. The second probability, which is the extension of the first probability, is the relative commutativity degree of a subgroup of a group. So if G is a finite group and H is a subgroup of G, so the relative commutativity degree of H in G, which we can denote by D H comma G, can be defined as the number of pairs H G. You know, H is in subgroup H and G in G. So number of pairs of H and G. So number of elements of H can be commuted with G. We can just compute the number of these pairs by the number of such pairs. Total number is order of H times order of G. So the relative commutativity degree of H in G is the size of matrix, size of set of pairs H comma G in H cross G, which HG is equal to GH, H and G commute, divide by order of H, order of G. So that's the relative commutativity degree. It means that for any subgroup H, we can compute the relative commutativity degree for this subgroup in G, comparing to G, right? And you can see that if H is G, so dG comma G is the usual commutativity degree. So we can say that the dH comma G is the generalization of the commutativity degree. Now let us give some examples. The first and very easy example is that if G is a group and H is the center, so obviously the relative commutativity degree H and G is 1, because if H is the center, it means that any elements in H can be commuted with all elements of G because it is in the center. So all elements of H will commute with all elements of G, so the relative commutativity degree is 1. Now, if S3 is the symmetric group of order 6 and take H is a subgroup of order 2, consists of 2 elements, identity and cycle 1, 2. The relative commutativity degree of H and H3, you can see that we have 8 pairs, you know, identity. So the first entries must be in H, so E and E, E and 1, 2, E 1, 3, E 2, 3. So we have 6 pairs because identity will commute with all 6 elements in S3. And 1, 2, we have only 2 cases. 1, 2 can be commute with identity, and 1, 2, not anymore. So the relative commutativity degree of H in S3 is 8 over 12 is 2 over 3. For dihedral group of order 8, if H is a subgroup of order 2, consists of identity and B. In dihedral group, you can see dihedral group consists of 8 elements: E, A square, A cube, B, AB, A square, B, and A cube, B. The commutativity degree of H in dihedral group of order 8, so we have to count all pairs, right? Now, again, if you take identity, E will commute with all 8 elements, so we have 8 elements here. But for B, if you take B, B can commute with identity, with itself, with B, with A square, because A square is the center, and A square, B. So we have 12 cases, so the relative commutativity degree of H in D8 is 3 over 4. We have also some results about the relative commutativity degree. So the first result is just showing, comparing the relative commutativity degree and the commutativity degree of whole group and the commutativity degree of subgroup. So as you can see, the relative commutativity degree of H in G is between the commutativity degree of G and the commutativity degree of H. It's interesting to compare the commutativity, the relative commutativity of a group with the quotient. So if G is a group, and if we have H and N are 2 subgroups, such that N is a normal subgroup and N contained in H, then the relative commutativity degree of HG is at most the multiplication of the commutativity, the relative commutativity degree of H over N in G over N times the commutativity degree of N. And also, if we have 2 groups, G1 and G2, and if we have 2 subgroups, H1 as a subgroup of G1 and H2 is a subgroup of G2, so the commutativity degree of G1, direct product of G1 and G2, is the multiplication of their commutativity degrees, and similarly for the subgroups, and also the relative commutativity degree of direct product of H1 and H2 in G1, direct product to G2 is the multiplication of relative commutativity degree. The next result for the relative commutativity degree is that if G is a non-abelian group and P is the smallest prime number dividing the order of G, and if H is a subgroup of G, then we have these properties. So if H is contained in the center, so as I mentioned before, it's obvious that the relative commutativity degree is 1. If H is not in the center, is not contained in the center, so we have two cases. If H is abelian, so we will have the upper bound 2p minus 1 over p square, right? And if H is not abelian, so we will have p square plus p minus 1 over p cubed. And you can see that we have a lower and upper bound for the relative commutativity degree, right? So the relative commutativity degree of H in H is between this as a lower bound and upper bound. And also this is an upper bound for the relative commutativity degree, and it's interesting to see that if the relative commutativity degree of subgroup H in G is exactly 3 over 4, then we should have H over the center of G intersection to H is a cyclic group of order 2. And if the relative commutativity degree is 5 over 8 and H is not abelian, then the the quotient H over the center of G intersection of H is isomorphic to Z2 cross Z2, which is a non-cyclic group of order 4. Okay, now I'm not going to just go deeply in any probability, because if we are going to define a probability and just seeing that what's the results and what's the property of this probability, we cannot enough time to introduce some more probabilities. I'm interested to give some definition of new probabilities, and then you can follow by the same method as I mentioned here to find the probability for some small groups, for some classes of groups, right? And find upper bound or lower bound and something else. So from now to the end of this lecture, I just want to introduce some new probabilities. This is defined by myself, and if you are interested to do something on these probabilities, just you can keep in touch with me to do some joint work on these probabilities. Okay, now the third probability is the square commutativity degree. What's the meaning of square commutativity degree? As I mentioned about the commutativity degree, the commutativity degree is the set of pairs xy such that xy equal to yx. But here I put these conditions that the set of pairs xy such that xy square is equal to yx square. You know, if xy equal to yx, so obviously xy square is equal to yx square. But sometimes we may have x and y are not commute. For example, xy is not equal to yx, but xy and yx are elements of order 2. because if they are elements of order 2, so the S square of any elements of order 2 is identity, so we have the equality. So I denote this probability by D2 of G. So D2 of G is the S square commutativity degree, is the set of all pairs X, Y in G cross G such that X, Y square is equal to Yx square divided by order of G square. It's the S square commutativity degree. For example, if you say S3 for the symmetric group, you know, if you take identity elements, so for the identity elements we have 6 elements. Identity will commute with, you know, if we have the commutativity, so obviously the S square of 2 commuting pair satisfying these conditions, right? So we at least have the pairs of commuting plus something else. For example, if you take 1, 3, 2, 1, 2, look at here, 1, 3, 2, 1, 2, 1, 3, 2, 1, 2, 2, 3, they are not commute. 1, 2, 3 cannot commute with 2, 3. But 1, 2, 1, 3, 2 times 2, 3 is a cycle of length 2. And 2, 3 times 1, 3, 2 is again a cycle of length 2. Right? So you can see that the S square of multiplication of 1, 3, 2, 2, 3 and 2, 3, 1, 3, 2 equal. So we have this pair as a pair satisfying this condition. So the S square commutativity degree for S3 is 5/6. You know, the commutativity degree of S3 is 1/2. But here we have some more pairs satisfying this condition. So it's 5/6. It's much bigger than half, right? So the commutativity degree of S3 is always less than the S square commutativity degree. Now, as I introduce the relative commutativity degree, now we can define the S square relative commutativity degree. So the S square relative commutativity degree is that if G is a finite group and H is a subgroup of G, so the S square relative commutativity degree denoted by D sub 2 HG is the set of all pairs HG in H cross G such that HG square is equal to GH square divided by order of H times order of G. And if you take H is G, then you will get the S square commutativity degree. Right. Now, what I suggest you is that you can replace N is 2 by, for example, 3. So you can define the not a square cube commutativity degree. Cube commutativity degree means that the set of all pairs xy such that xy cubed is equal to yx cubed defined by order of G square. Or even you can define the the n's commutativity degree, right? Just considering the condition xy to the n is equal to yx to the n. So, you know, there are many work on this area. You can start from 2 and then continue for n is 3, n is 4, and so on. And you can also compare this uh, uh, list of commutativity degrees in terms of n as a sequence. And similarly for the relative commutativity degree in these cases, right? So that's the new definition, and you can deal with it. There are many works you can do on this work. For example, if you just see the square commutativity degree, so let me say some questions. What's the square commutativity degree for, we can compute it for S3. What's for Sn in general? What we can say about alternating group for An? How about the square commutativity degree for dihedral group of order 2 times n? For quaternion group or generalized quaternion group, you know, there are many groups. You can just focus on these groups and find that the exact value, or sometimes maybe you can find lower or upper bound for this amount. Okay, now let me just move to another probability. The probability number 1 is co-prime degree of a group. This is also the new probability which I define here. Suppose that G is a finite group. The co-prime degree of G, which we can denote it by P co-prime of G, defined as the following ratio. So the co-prime degree of G is the set of all pairs x, y in G cross G, such that order of x and order of y are co-prime. Now let me say again, the set of all pairs x and y such that order of x and order of y are co-prime. So the set of all pairs of co-prime orders, co-prime order of elements of G, divide by order of G square. Now look at the dihedral group of order 8. We have 8 elements here. So if you take these 8 elements, right, and order of elements of D8. So identity has order 1, A has order 4, A square has order 2, A cube has order 4, right? B has order 2, AB has order 2, A square B and A cube B, that's all of order 2. Now, what's the number of pairs of co-prime orders? So if we take identity, because identity has order 1, so 1 is co-prime with all other orders. So we have 8 elements here, right? E and identity. So now, how about other elements? If we take, for example, A, so what we can say about the other elements? A can also have with identity, not anymore. A square also with identity, because they have order 4, so we have another 8. So we have here 8 elements. Here we have A with A square with A, so we have 7 elements. So I have to add something more here. So I have to correct this one. I mentioned the coprime degree of a group G is the set of pairs x, y, which the order of x and y are coprime, right? Now, for example, dihedral group of order 8, I corrected here. So we have 8 elements in D8, right? So if you take the identity element, the order of identity is 1, so 1 with other order of other elements are coprime, so we have the pair E, comma E, EA, EA square, EA cube, EB, EAB, EA square B, and EA cube B. Now we have again A can only coprime with the identity, A square also with identity, A cube an identity, BE, ABE, A cube BE, A square BE, and A cube BE. So we have 15 pairs divided by the order of all pairs is 64. So the coprime degree of the dihedral group of order 8 is 15 over 64. Now the non-coprime degree of a group G is the complement of the coprime degree, which is the set of all x and y in G such that order of x and order of y are not coprime, right? So it's easy to see that the non-coprime degree of a group G is 1 minus the coprime degree of G. So for example, for the dihedral group of order 8, we find 15 over 64 as the coprime degree. So the non-coprime degree of the dihedral group is 1 minus 15 over 64 is 49 over 64. Now the probability number 7. Probability of a subgroup to be a normal. You know the definition of normal subgroup, right? So suppose that G is a group and H is a subgroup. So the probability of subgroup H to be a normal, we can denote it by P normal of H, and we can define it as this definition. This is the set of all elements of G, such that we have this property, G inverse HG is H. If we have for all elements of G, if we have G inverse HG is H, then H is normal. So if H is normal, so obviously this probability is 1. But if H is not normal, so we have some elements in G which has not this property. So the number of these elements of G divided by order of G is the probability of subgroup H to be a normal. For example, look at S3 again. We have 6 elements, and if you take H is a subgroup of order 3 and K is the subgroup of order 2, so it's clear that H is a normal subgroup of S3 because the index is 2. So the probability of subgroup H to be a normal is 1, but K is not normal. So for the probability for K, we can see that the only elements of S3 which has this property, G inverse KG is K, or similarly KG is GK. So the only elements which commute with K is the identity. So we will have 2 elements, identity and 1, 2. So we have 2 over 6 is 1 over 3. So this is the probability of subgroup H to be a normal. So this is important for knowing that if you take any arbitrary subgroup, so and if we are going to talk about the normal property, so if the probability is close to 1, it means that the subgroup is close to be a normal, and if the probability is close to 0, it means that it is far from to be a normal. Now the probability number 8 is the centrality degree of a group. What's the meaning of this probability? Suppose that G is a finite group and ZG is the center of G. So the centrality degree of G we can denote by PZ of G. It's defined as the following relation. You know, PZ of G is the set of all X and Y in G cross G, X and Y in G cross G, such that X, Y is in the center, divided by order of G square. Right? So you know that if X and Y are both in the center, so obviously the multiplication is also in the center. But if X is in the center, but Y is not in the center, or X and Y are not in the center, so we may have X, Y in the center or it's not. So we can just compute the number of pairs with this property. As an example, again, for S3, we have 6 elements. We know the center of S3 is the trivial subgroups. So the number of pairs X, Y in S3 cross S3, which X, Y is in the center, is equal to that all X, Y, which X, Y is the identity, because the center of S3 has the identity. So it means that X must be equal to Y inverse, right? So we have to count all elements X and Y such that X is Y inverse. So we will have, or Y is X inverse. So we have identity, because the inverse of identity is identity. 1, 2, 1, 2, 1, 3, 1, 3, 2, 3, 2, 3, 1, 2, 3, 1, 2, 1, 2, 3, 1, 3, 2, because 1, 3, 2 is the inverse of 1, 2, 3, and 1, 3, 2, 1, 2, 3, because 1, 2, 3 is the inverse of 1, 3, 2. So we have 6 pairs, so 6 over 36 is 1 over 6. And we can also compute it for the dihedral group of order 8. For dihedral group of order 8, you know the center is the center consists of 2 elements, identity and A square, right? So if we can compute the pair, we have two possibilities. XY is identity or XY is A square. So if we count these numbers, we will have 16 pairs divided by 8 square. So it's 2 over 8 is 1 over 4. Now, the last probability, because we don't have enough time to introduce some more. Of course, maybe in the second part, which is about the graph, I may introduce some more probability related to graphs. So the last probability related to a group is the central automorphism degree in a group. So what's the meaning of that? Suppose that G is a group and alpha is an automorphism. Automorphism means that alpha is a homomorphism from G to G, which is an isomorphism, is onto and one to one. It's called automorphism. So alpha is called central automorphism if we have this property. If we have G inverse, the image of G under alpha, alpha of G is in the center for all G in G. Right? If we have this property for the automorphism alpha, then alpha is called central automorphism. So you can see that if alpha is identity, we have this property, right? Because G inverse alpha, if alpha is identity, so G is G inverse G is the identity and is in the center. So the identity automorphism is always central automorphism. Now, by this definition, I'm going to define the central automorphism degree. So if G is a group and alpha is a fixed automorphism, the central automorphism degree of alpha in G, we can denote by P alpha of G, is defined as the number of elements G in G such that G inverse alpha of G is in the center divided by order of G. So it's obvious that if P alpha of G is 1, then alpha is the central automorphism. And similarly, the converse is true. If alpha is a central automorphism, then the probability centrality degree is 1, right? And also, we can see that these two sets, LG, ZG, is the set of all G in G with this property, with all alpha in automorphism of G, and set of all automorphism of G with this property with all G in G. There are two subgroups. The first one is subgroup of G, and the second one is the subgroup of automorphism of G. So we can use these two subgroups to find some lower or upper bound for this probability. Now, as I mentioned, for each of these probability, each of these 9 probabilities which I introduce here, of course, number 1 and 2, I gave some results, but for the others, you can compute this probability for some sort of groups like symmetric group, alternating group, dihedral group, and that's the generalized quaternion group. You can compare probability of group with the probability of subgroup, as I compared the probability for the commutativity degree of G and the subgroup G. No, you can do the same thing for other probabilities. You may find lower and upper bound for each of the probabilities. This is another research problems that you can try to do something. So it's also interesting to determine the probability, right, for direct product of two groups G1 and G2. So for each of these probabilities, you can compute the probability for dihedral group, not only for dihedral for direct product, not only for direct product of two groups, maybe for direct product of n groups, G1 cross G2 until Gn. And also, it's interesting to determine this probability for some important class of groups. You know, P groups is one of important class of groups. Nilpotent groups is also very, very important, soluble groups, and so on. So you can compute these probabilities for this sort of groups. So I just introduce some new ideas about the probability and groups. We can define some more probabilities, right? And also, you know, there are many work to do on this probability. So I hope that you got some ideas about the relations between probability and groups. You know, if we compare the probability of groups, so for groups we can compute the probability if we have the for example special values of a probability, so we can talk about the list of all groups with this probability, determine the just or classify groups with a specific number of probabilities. Okay, so thank you very much. In the just few minutes, it's the next 10 or 15 minutes, if you have any questions about this topic, I am just ready to explain about your question. Thank you very much indeed. All right.
Okay, that's very interesting, Professor Erfanian. Let us give an applause for him. Okay. And also, please accept our apologize for the inconvenience in the beginning of the video because the instability of our internet connection. We will share the recorded video after the algebra seminar. But of course, if there is something that confuses you, you can ask for questions to Professor Erfanian now. Okay, is there any question for this first session? You can use the raise hand feature on your Zoom or simply write down your question in the chat box. Okay. Okay, from ITB, Jericho Gormantara. Yeah, I will read his question. First of all, thank you for the interesting lecture, sir. There are so many divining tools such as relative commutativity degree, square commutativity degree, or cube commutativity degree, etc. I'm just wondering, sir, what's your motivation behind these divining tools? I mean, for example, if we can find the cube relative commutativity degree of dihedral group, then what we can say about this dihedral group by having that degree beside the definition of the degree? Thank you. That's the question, Professor.
Okay, thank you very much. Let me just say a few remarks on the motivation of these probabilities. We define probabilities and we can find some properties of this probability. But the motivation of the probability is that to use the tool of probability to prove some theorems, some theorems in group theory. You remember I mentioned that if the commutativity degree is bigger than half, then the group G is nilpotent. You know that we have a theorem which says that if G is an abelian group, then the group G is nilpotent. But if we replace the abelian property by non-abelian group, but with the commutativity degree bigger than half, we can give a strong theorem because you extend the theorem which says that if G is abelian, then G is nilpotent. You replace the abelian property not only for abelian, for non-abelian group with the commutativity bigger than half, right? So it's very important to use this sort of probability, this amount of probabilities to give some relations between some important properties in groups, right? For P groups, we have many theorems about P groups. For nilpotent groups, soluble groups, we have many properties, many theorems in group theory. So our motivation is that to use this very easy tool of probability to improve some theorems. This is my motivation. And if you can do you can improve at least one theorem, it's very interesting because you can use an easy tool for an important theorem. So that's a motivation for each probability.
All right, thank you so much for the answer, Professor. Is it clear, Jericho? I think it is clear. And then there is a second question for you, Professor, from Universitas Pertamina, Rangga Nugraha. I found one of your results is very interesting. That is, if the commutative degree of a finite group is bigger than 5, 8, then the group is commutative. It means that if we want to prove that a finite group is commutative, then it is enough to prove 5 to 8 of all pairs of all pairs elements of the group. Can you show us how you prove this theorem? Just a sketch, maybe. When are you define this commutative degree? In what year?
Okay, so as I mentioned, if the group G is non-abelian, so the commutativity degree is less than or equal 5/8. Now, the equivalent theorem with this theorem, it says that if we have a group with the commutativity degree bigger than half, then the group is abelian. So what's the meaning of that? Suppose that you have a finite group. You can find by computer, we have some softwares like GAP or Cayley or Magma. So you can find the number of pairs which are commute, right? Divide by order of G square. So when you pass 5/8, then you don't need to compute the rest, but that's enough to say that the group is abelian. So that's as an algorithm, which you can, because sometimes the group is very big. So we have many computations to find the all commuting pairs. So if you find the commuting pairs with the order of G square, is bigger than 5/8, that's enough to see that the group is abelian. So you don't need to check all other pairs. That's the motivation.
Okay, that's very interesting. So, okay. Is there any question? Maybe one more question for this session. Okay. Okay. If there is no other question, actually, I have one question. Oh yeah, first I will introduce again myself. My name is Fitri, Professor. I have just graduated from ITB. My question is about the commutativity degree. We know that each element of a group obviously will be commute with the identity element and its inverse, right? So it means we can have the commutativity degree of a group to be 0, right, Professor? Even for the non-abelian group. So what I am curious about is, can we have the lower bound of the commutativity degree of a group? I have a hypothesis that the lower bound must be 2 times its number of elements, minus 1 or 2 maybe, and divide by the order. Actually, I haven't made a detailed calculation, just a hypothesis. That's my question.
Okay, thank you very much for your question. It's very important note that the commutativity degree cannot be 0, because we at least have identity elements, which identity commute with all elements. So the number of the at least number of commuting pairs is order of G. So the lower bound is order of G divided by order of G squared. So it's 1 over the order of G. But this lower bound is not so good, because we may have some more pairs, right? This is the at least just a lower bound. It's not the sharp, but this is the lower bound, and this means that the commutativity degree is if you take a non-abelian group, right? So the commutativity degree is between 1 and 5/8. Between not 1, between 1 over the order of G, right, and 5/8. So the commutativity degree is in this segment, right? 1 over the order of G and 5/8. So let me say one of the important questions for the commutativity degree. It's interesting to see that if we have, as I mentioned, the commutativity degree is between 1 over the order of G and 5/8. Take any arbitrary, not only integer, just arbitrary number between 1 over order of G and 5/8, right? For example, 1/2, 1/t, and something like that. We may consider the rational number or irrational number. So the point is that, does there exist a group G with the exact value of that commutativity degree? For example, if we take 1 over 1,000, right? So, and assume that this number is between the segment which I mentioned, do we have any group with the commutativity degree of exactly 1 over 1,000? And let me say some more other questions. So if you take a specific number, do we have a sequence of groups with the commutativity degree? You can say the commutativity degree, for example, AN, such that AN tends to the specific number. So we can combine just limit of a limit of a sequence to that number. So it means that we can combine analysis here, right? To see that what will happen for the for the amount of commutativity degree for all groups. So what do we have a huge group with this amount of commutativity degrees or not? So there are some questions about this sort of questions about the exact value of the commutativity degree. But you are right, yes, we have a lower bound and the commutativity degree cannot be 0.
Okay, thank you so much, Professor Erfanian. I think that's all for the first session. Again, thank you so much for Professor Erfanian and also for all participants. Okay, we will have a break for 50 minutes until 13:10 in GMT +7. I mean, if possible, please stay in this Zoom meeting. You can turn off your camera and also your microphone. Okay, so
Thank you very much indeed.
Thank you so much. Okay, ladies and gentlemen, we will back to the next session in a minute. So please get back to your seat, turn on your camera, and take your note. Thank you. Okay, good afternoon, everyone. So, how's your break? I hope it refreshes you and makes you ready for the next session. Okay, we will go to the second subtopic.
Let me start the second part of my lecture.
Okay. Yeah, we will go to the second subtopic of Professor Erfanian's talk. It is about graphs, probability, and groups. And I think Professor Erfanian is already here with us. So we can start the second session now. Here it is. Enjoy.
As I mentioned this morning, I'm going to give some relations between four important concepts: groups, probability, graphs, and matrices. In my first part of lecture, as you remember, I introduced some probabilities associated to groups. So I gave some probabilities for a given group, and I mentioned some result about this. Now, in the second part of my lecture, I would like to add one more concept, one more important concept, which is graph. So I would like to add graph to the probability and groups. This is the just title of my second part of talk. So I'm going to give a brief description on graphs at first, and then introduce some graphs associated to groups, and finally give some relations between probability, graphs, and groups. Okay. As you know, when we are talking about the graph, it means that we have a set we denote by V as a vertex set, and just another set which is the edge set. Vertex set means that we have some nodes, and between any of two nodes, the edge set will determine that there exists an relation between two nodes which we denote by an edge. So if we are talking about the graph, It means that we have to know about the vertex set and edge set. Sometimes we may have a rule between two vertices to have an edge, right? So there are some basic definition about the graph. If we have a vertex x which is adjacent to itself, we can say it's a loop, right? And sometimes we may have more than one edges between two vertices. In this case, we can say multiple edges or parallel edges. Now, in this lecture, in whole of this lecture, we always assume that the graph is simple. So when we are talking about simple graph, it means that we have two important conditions. The first condition is that we don't have any loop. So any vertex cannot be adjacent to itself. We don't have any loop. And also we don't have any multiple edges. So between any of two vertices, we will have at most one edge between them. By these two conditions, we can say that the graph is simple graph. Sometimes we may have a direction in a simple graph. Its direction means that vertex x is adjacent to vertex y, but it's not necessarily y is adjacent to x. And sometimes, especially in this part of my talk, I assume that the graph is simple and undirected. Undirected means that between any of two vertices x and y, so if we have an edge between x and y, it doesn't matter, it is not different that to say x is adjacent to y or y is adjacent to x. So it means that between x and y, we have an edge. So we don't mention anything about direction. When we talk about the connected graph means that if we have two arbitrary vertices like x and y, if there exists at least a path between x to y, path means that we have some vertices like t1, t2, tk, such that x is adjacent to vertex t1, t1 adjacent to t2, until tk and y. So this is the path between x and y. So if for any two arbitrary vertices we have a path between x and y, then we say that the graph is connected. Otherwise, the graph is not connected and we may have some components, some connected components. The distance between any of two vertices is the length of shortest paths, because we may have some paths between x and y, so the length of shortest paths between x and y is called the distance. For any graph gamma, we may have diameter. Diameter of a graph means that the maximum distance between any of two arbitrary vertices in graph, right? The maximum distance is a diameter. And we may have a girth. Girth means that if we have a cycle, if we have at least a cycle in a graph, the length of shortest cycle is called the girth. So it's clear that the minimum value of girth is 3, because the shortest cycle is a cycle of length 3. And sometimes if we may have no cycle, for example, If we have a tree, we don't have any cycle. In this case, the girth is denoted by infinity. We may have many important graphs. We may have complete graph. Complete graph means that all vertices are adjacent together. We may have complete bipartite graph. It means that we have two independent sets such that for any edge should be one ends in the first set and another ends in the second set, because in bipartite graph the vertex set partitioned into two disjoint sets. Anyway, we don't have enough time to give more details about the graph, so maybe that's enough to start the main topic of this lecture, which is graph associated to groups. Okay, so I'm going to introduce some graphs related to groups. The first and just important graphs which are related to a group is called commuting and non-commuting graph. You remember I defined the commutativity degree for a given group G. So I will introduce the commuting and non-commuting graph, and then we'll give a relation between the commutativity degree and also the commuting or non-commuting graph. All right, let me define the non-commuting graph first. So suppose that G is a finite group and Z of G is the center of group G. The non-commuting graph of G, we may denote it by gamma G, is undirected simple graph with the following vertex set and edge between two vertices. The vertex set of non-commuting graph is the set of all non-central elements of G. Non-central elements means G minus the center. So all elements in G minus the center of G is called non-central elements, and this is a vertex set. And if we have two non-central elements, if we have two vertices X and Y, then we can say that X is adjacent to Y if and only if XY is not equal to YX. It means that X and Y cannot commute. The complement of non-commuting graph is called commuting graph. So by definition, the commuting graph is a complement of non-commuting graph, which means that the vertex set, we have the same vertex set, so the vertex set for the commuting graph is also non-central elements, so it's G minus the center, and two elements X and Y are adjacent if and only if XY is equal to YX. For non-commuting graph, we had XY not equal to YX, but here for commuting graph is XY is equal to YX. So commuting graph is the complement of non-commuting graph. Let me give some examples. Suppose that S3 is a symmetric group of order 6. So we have 6 elements, right? The center of S3 is trivial. is identity only. Now, how about the non-commuting graph of S3? So as I mentioned, the vertex set of non-commuting graph is of S3 is S3 minus the center of S3. So S3 has 6 elements and the center is identity, so we have to remove identity from the S3. So we will have 5 vertices: 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. Now, how about the non-commuting graph? We have 5 vertices, right? Now, you can see that, for example, 1, 2 is adjacent to 1, 3. Why? Because 1, 2 times 1, 3 is not equal to 1, 3 times 1, 2. And you can see that we don't have any edge between 1, 2, 3 and 1, 3, 2, because 1, 2, 3 is the inverse of 1, 3, 2. And we know that 1, 2, 3 and 1, 3, 2 are commute. So since they are commute, we don't have any edge. So you can easily check the other vertices, and you can see that here we have 9 edges for the non-commuting graph of S3. Now, how about the complement of non-commuting graph, which is we denote by gamma S3 bar? So here, you have to just consider the complement of this graph. The complement of this graph is only one edge between 1, 2, 3 and 1, 3, 2, and 3 isolated vertices. So we will have only one edge for the commuting graph. Let me give another example. Look at dihedral group of order 8. So we have 8 elements, right? And the center consists of 2 elements, identity and A square. So the vertex set for the non-commuting graph of the dihedral group is the set of all non-central elements. So we have to remove identity and A square, which are in the center, from the set of elements of the dihedral group. So we will have 6 vertices. We have A cubed, B, AB, A square B, and A cube B. And here you can see the edges. For example, between A and B, we will have an edge because AB is not equal to BA. But we don't have edge between A and A cube because A times A cube is A to the 4, which is identity. And A3, A to the 3, A cube times A is again A to the 4 is identity. So A and A cube are commute. So we don't have edge here. The number of edges for the non-commuting graph of the dihedral group is 12. Now, the complement of non-commuting graph of the dihedral group consists of 3 edges, right? So we will have 3 edges for the commuting graph of the dihedral group of order 8, or is a complement of non-commuting graph. We have the same situation for the quaternion group of order 8, you can see we have two elements, 1 and I minus 1 in the center of quaternion group of order 8, and we have 8 elements as the set of elements of quaternion group. So we will have 6 vertices for non-commuting graph. You can see I minus I, j minus j, k minus k, and again here we will have 12 elements. And the complement of non-commuting graph consists of 3 edges. Okay, now let me just start discussion about the probability graph and group. The important matter here is to find a relation between the commutativity degree, which I defined in my previous lecture, and commuting or non-commuting graph here. Let me just remind the commutativity degree again here, right? So the commutativity degree is the set of all pairs x and y such that x and y are commute divided by order of g squared. Now, I'm going to give a relation between the commutativity degree and the number of edges for non-commuting graph or even for commuting graph. Now, look at here. Suppose that A is the set of all pairs x and y which are commute, and B is the set of all x and y which are not commute. So the G cross G is the set of all pairs can be partitioned into two disjoint sets A and B. Okay, now by this equation we can see that order of G square is order of A plus order of B. Now, but look at set A. Set A is the set of pairs x and y such that xy equal to yx. And if you look the commutativity degree, on the top, we have exactly this set. So the commutativity degree is the size of set A over order of G squared. So by this equation, we can write order of A, set A is equal to order of G squared times the commutativity degree. So on the other way, look at set B. Set B is the set of all pairs x and y, which x and y are not commute. So you can see that, first of all, x and y cannot be equal, because if x equal to y, then obviously x and y commute, so x cannot be equal to y, right? It means that we will not any loop, and if x and y are not commute, then we will have an edge. So the size of set B is the 2 times the number of edges of non-commuting graph. Because, we have x and y, if x and y are not commute. So we will have x and y and x. So we have 2 pairs. So for any 2 pairs, we will have 1 edge, right? because we don't have any direction. So the size of B is 2 times of the number of edges. Now, by the above equation, which order of G square is order of A plus order of B, we can see that order of G square is order of A plus order of B is equal to order of A is order of G square times the commutativity degree, as we denote by equation number 1, plus order of B is 2 times the number of edges of non-commuting graph. So plus 2 times the number of edges. So from this equation, we will get the number of edges of non-commuting graph is half of order of G square times 1 minus the commutativity degree. So the same, we may find the similar equation in terms of the set of size of set of commuting graph. Okay, now let me give some examples. Again, look at the non-commuting graph of S3. So as I mentioned at the beginning of my talk, so the non-commuting graph consists of S3, consists of 5 vertices, right? And we will have the number of edges is 9. But if you remember, in my previous lecture, I found the commutativity of S3. So the commutativity of S3 was 1 over 2. By the formula as I gave here, so the number of edges for the non-commuting graph of S3 is half of order of S3 square, 1 minus the commutativity of S3, and you can see that we can find exactly 9 edges, as you can see here. So this is the relation between the commutativity degree and the number of edges of non-commuting graph. Similarly, for dihedral group of order 8, we have already found the number of edges is 12. Now, if in this formula, if we put the 12 for the number of edges, we can find the commutativity degree of dihedral group. So as you can see by this equation, the commutativity degree of dihedral group is 5 over 8. And you remember that in my first part of my lecture, I found the commutativity degree of dihedral group is 5 over 8. 5 over 8 is the biggest value of commutativity degree for non-abelian group, because 5 over 8 was the upper bound for a non-abelian group. So, the important thing for the relation between the commutativity degree and the number of edges of non-commuting graph is that by this formula, let me just look at this formula. So this formula, if we have the exact value of the commutativity degree, then obviously we will get the exact number of edges for non-commuting graph. If we have an upper bound for the commutativity degree, for example, we know for non-abelian group we gave the upper bound 5/8. So if we'll have upper bound for the commutativity degree, then we will get a lower bound for the number of edges of non-commuting graph. And if we have a lower bound for the commutativity degree, then we will get upper bound for the number of edges. For example, we know that if we have a graph with n vertices, so the utmost number of edges is n times n minus 1 over 2, which is the complete graph. So this is the upper bound for the number of edges. By this upper bound, we can get a lower bound for the commutativity degree. So this is important to find lower bound or upper bound for the commutativity degree or for the number of edges. For example, we can give this very easy and simple theorem that if G is a finite non-abelian group, then the number of edges of non-commuting graph is bigger than or equal to 3/16 times order of G square. So the proof follows from this point that the upper bound for the commutativity degree of non-abelian group is 5/8. So it's enough to put 5/8 in the formula as I gave before. So you can easily find 3/16 order of G square. And also we can give a lower bound for the commutativity degree by knowing that if you look the vertex set of non-commuting graph, so the size of vertex set is order of G minus order of the center. This is the number of, if you put n for this number, so the utmost number of edges for any graph with n vertices in n times n minus 1 over 2. So by this upper bound for the number of edges, if you put here, then we can get a lower bound for the commutativity degree. Now, let me give some results about non-commuting graph. So suppose that G is a finite non-abelian group. So the non-commuting graph has no isolated vertex. It means that if you take any vertex, so it will be adjacent to at least one vertex. The second property of this graph is that the graph is always connected. The diameter is 2, the girth is 3, and also the graph is Hamiltonian. Hamiltonian means that we can have a cycle which pass all vertices just only one time. If we have such cycle, then we can say that this cycle is a Hamiltonian, and if a graph has a Hamiltonian cycle, then the graph is Hamiltonian. Also, the graph, non-commuting graph, is planar. Planar means that we can be able to draw a graph in such a way that we don't have any intersection between any two edges. The only possibility for intersection of two edges is the just end vertices. If we have this situation, then the graph is called planar. So we can prove that the non-commuting graph is planar if and only if G is one of these three groups: symmetric group of order 6, dihedral group of order 8, or quaternion group of order 8. The proof is easy. I wrote down the proof, but I think we don't have time to mention the proof. The first part, the first part I proved that if you take an arbitrary vertex x, then the degree of x is bigger than or equal to 1. So it means that if we have vertex x in non-commuting graph, because the vertex set is G minus the center, so x is not in the center. Since x is not in the center, so there exists at least one elements in G we call y, such that x and y are not commute. So since x and y are not commute, so it means that y is not in the center, so y is in G minus the center, and it means that y is a vertex. And since xy not equal to yx, so x is adjacent to y. So for any arbitrary vertex x, we can find vertex y such that x is adjacent to y. So the degree of x is at least 1. It means that x is not isolated vertex. For the second part, which is the connectivity property, is that if we take two elements x and y, two arbitrary elements x and y. So first of all, just let me give the outline of proof. First of all, by the previous part, x and y are not isolated vertex. So if x is adjacent to y, so it means that we have a path between x and y. So the proof is completed. If x is not adjacent to y, so we have an elements xy and yy in the vertex such that x is adjacent to xy and y is adjacent to y1. Now, if x is adjacent to y1, then we will have a path x, y1, y. Or even if y is adjacent to xy, again we will have x, x1, y as a path between x and y. So assume that x is not adjacent to y1 and y is not adjacent to xy. In this case, we can prove that x is adjacent to a vertex xy, y1, and xy, y1 is adjacent to y. So we will have a path of length 2 between x and y. This proves that the graph is connected, and also we can see that the diameter is at most 2, and we can prove that the diameter cannot be 1, because if the diameter is 1, then it means that the graph is complete, and here the graph cannot be complete. Okay, so let me just pass the proof. For the planar, the non-commuting graph of S3, let me show the look at here. This is the non-commuting graph of S3. Here you can see that by this just this way, some edges, for example, edges between 1, 3 and 1, 3, 2, and edges and edge 1, 2, 2, 3, they have intersect. but we can draw this graph in such a way that they have no intersection. So I just consider the graph in this case, this is exactly the non-commuting graph, but for example, vertex between 1, 2, and 1, 3, I draw from this way, So you cannot find any two vertices which has any intersection. So the non-commuting graph of S3 is planar, and similarly for dihedral group of order 8, also you can see we draw the graph such that there is no intersection between edges, and similarly for the non-commuting graph of quaternion group of order 8. Okay, let me give some problems just very quickly. It's important to see that if we have two isomorphism group, then the non-commuting graph are isomorphism, but the inverse is not true. So the problem is that if we have two non-commuting, two non-abelian groups, G1 and G2, such that the non-commuting graph of G1 and G2 are isomorphic, can we say that order of G1 and order of G2 is equal? It means that G1 and G2 have the same order, or in what condition we can say that they have the same size? And also you can just deal with these questions that if G is a finite non-abelian simple group means that there is no non-trivial normal subgroup, right? So the only normal subgroup is identity and the whole group. So if G is a finite non-abelian simple group, and if we have isomorphism between non-commuting graph of group G and non-commuting graph of H, so can we say that H is also non-abelian and simple? So it means that by the isomorphism between two non-commuting graphs, can we follow a property from G to H? For instance, here we are talking about the simple group. So G is simple, implies that H is simple. Also, it's interesting to determine the graph in the general case for dihedral group of order 2 times n, or symmetric group and alternating group. We have some questions that do we have any group such that the non-commuting graph of the group G is complete graph? Does there exist any group that the non-commuting graph is complete graph? Or the same question to have complete bipartite graph or regular graph? There are some questions that you can just investigate about the group and maybe find a classification of group satisfying in these conditions. Okay. As I define the relative commutativity degree, here we can also define the relative non-commuting graph. So the relative non-commuting graph means that we can define non-commuting graph related to a subgroup H of a group G. So let me give the definition. Suppose that G is a finite group and H is a subgroup of G. The relative non-commuting graph of subgroup H of G we may denote by gamma HG. It's undirected simple graph. The vertex set is G minus the centralizer of H in G, and two vertices X and Y are adjacent if we have two conditions. The first one is that X and Y are not commute, and the second condition is that one of X or Y should be in H. So here you can see the vertex set is G minus the centralizer of H in G. The centralizer of subgroup H in G is the set of all elements in G such that G and H are commutate, H and G and H are commute with all elements H in capital H. So X is adjacent to Y, as I mentioned here. X or Y, at least one of them, is in H, and X, Y not equal to YX. As example, if we take symmetric group S3, we have 6 elements. Now I consider 2 subgroups. The H is subgroup of order 2, consists of 2 elements, identity and transposition 1, 2. And K is a subgroup of order 3, consists of 3 elements, identity 1, 2, 3, and 1, 3, 2. Now, the centralizer of H in S3 is the whole subgroup H, right? The only elements of S3 which commute with identity and 1, 2 is only identity and 1, 2. And similarly for the centralizer of subgroup K is also K. So the relative non-commuting graph of H in S3 consists of 4 vertices. You know, the vertex set is S3 minus the centralizer of H in S3. So S3 has 6 elements and H has 2 elements, so we will have 4 vertices. So we have 4 isolated vertices, and for the relative non-commuting graph of K in S3, we have 3 isolated vertices. You can see that if H is abelian group, then the centralizer of H in G consists of H. And because we remove the centralizer of H in G, so it means that in the vertex set we don't have any elements in H. So in this case we will have some isolated vertices. Now let me give a relation between the relative commutativity degree and the number of edges of non-commuting graph of relative non-commuting graph of H in G. If G is a finite group and H is a subgroup of G, then we can easily find that the number of edges of relative non-commuting graph of H in G is order of H times order of G times 1 minus the relative commutativity degree of H in G minus order of H square over 2 times 1 minus the commutativity degree of H. You can see that the number of edges of the relative commutativity, relative non-commuting graph associated to the relative commutativity degree of H in G and the commutativity degree of H. So you can see that if H is non-abelian subgroup, here is formula if H is non-abelian subgroup. If H is abelian, so we will have no H, so the number of edges is 0. So as I mentioned, for the relation between commutativity degree and the number of edges of non-commuting graph, here also we can find the lower bound or upper bound for the number of edges of relative non-commuting graph by having lower or upper bound for the relative commutativity degree of H in G and the commutativity degree of H. Here is a lower bound for the number of edges of non-commuting graph. And here also is an upper bound for the number of edges. And also, you remember that we mentioned about the relative commutativity degree in some special cases. For instance, here if H over H intersection to the center isomorphic to the non-cyclic group of order 4, right? Then we can find the relative commutativity degree of H, right? And also we have a lower bound for the commutativity degree of H, so we will get the lower bound for the number of edges of non-commuting graph. So it's interesting to prove that we cannot find any non-abelian group and subgroup H such that the non-commuting graph of H in G is complete graph, and the same situation we don't have any group G and subgroup H of G with the non-commuting graph is completed by partite graph. For the isomorphism, we can prove that if H is a non-abelian subgroup of group G, such that the relative non-commuting graph of H in G is isomorphic to the non-commuting graph of symmetric group Sn, then if the size of centralizer of H in G is at most n, then we can prove that order of G is equal to order of Sn, and for small values n is 3, 4, and 5, we can even prove that G is isomorphic to symmetric group of Sn. Okay. For any non-abelian group G and subgroup H with the center of H is trivial, we can prove that the diameter of non-commuting graph is 2 and girth is 3, just similar to the non-commuting graph. Now some exercises about the relative commutativity degree. So you can draw the relative commutativity degree of alternating group of order 12 is A4 in the symmetric group of order 4, 24, right? And the second question is that can we say that for any non-abelian group G and subgroup H of G, the relative non-commuting graph gamma HG is Hamiltonian, or what we can say about the planarity? And also, if we have two isomorphism non-commuting graph gamma H1 G1 and H2 G2, and if H1 minus the center of H1 has the same size of the H2 minus the center of H2, can we say that H1 and H2 have the same order? Okay. Now, let me give a new graph related to a group. You remember I defined the coprime degree in my first lecture. Now I'm going to define the coprime graph for a group G. Let me introduce this graph. Suppose that G is a finite group, right? So the coprime graph of the group G, which we denote by gamma coprime G, is a graph with the vertex set is the whole elements of G, and two elements X and Y, two distinct elements X and Y, are adjacent if and only if they have coprime order. It means that the order of X and order of Y are coprime. If we have this situation, then we will have an edge between two vertices X and Y. This is coprime graph. Now, let me give example. Look at symmetric group of order 6. We have 6 elements, right? The order of elements here I have written here. So identity has order 1, 1, 2, 1, 3, 2, 3 have order 2, and two elements 1, 2, 3 and 1, 3, 2 have order 3. So we have 6 elements, and so since the vertex set of coprime graph is the whole set of elements of the group, so we have 6 vertices here: identity 1, 2, 1, 3, 2, 3, 1, 2, 3 and 1, 3, 2. Now look at here. Identity will adjacent to all other vertices, because identity has order 1, and 1 with any order of any elements is coprime, right? So identity adjacent to 1, 2, 1, 3, 2, 3, 1, 2, 3 and 1, 3, 2. Now how about 1, 2? 1, 2, well, obviously is adjacent to identity, and also 1, 2 is adjacent to 1, 2, 3 and 1, 3, 2, because 1, 2 has order 2, and 1, 2, 3 or 1, 2, 1, 3, 2 has order 3, and 2 and 3 are coprime. So 1, 2 is adjacent to 1, 3, 2, 1, 2, 3, and similarly 1, 3 and 2, 3 are adjacent to 1, 2, 3 and 1, 3, 2. But there is no edge between 1, 2 and 1, 3, because they have order 2, and 2 and 2 are not coprime, right? And also between 1, 2, 3 and 1, 3, 2 there is no edge, because 3 and 3 they are not coprime. the greatest common divisor is 3. So this is the co-prime graph of S3. You can see that we have here 11 edges for the symmetric group of order 3. Now, look at Z4. Z4 is a group of order 4. We have 0 bar, 1 bar, 2 bar, 3 bar. So the order of 0 bar is 1. Order of 1 bar is 4. You know, Z4 is the additive group. So 1, 4, we should add 1 for 4 times. 1 bar plus 1 bar plus 1 bar plus 1 bar is 0. So order of 1 bar is 4, order of 2 bar is 2, and order of 3 bar is 4. And you can see that the only edge which we have is between the identity elements, between 0 bar and other elements, 1 bar, 2 bar, and 3 bar. We don't have any edge between 1 bar and 3 bar, or 1 bar, 2 bar, and 2 bar, 3 bar, because 1 bar and 2 bar, so they are not co-prime. The common greatest common divisor of 4 and 2 is 2. So this is a cycle. This is a star graph. A star graph, if we can denote by K13, and we have 3 edges. For dihedral group of order 8, we have the same situation. Again, we will have a star graph, right? So the only identity elements can adjacent to all other vertices. We don't have any more edges here, so we will have 7 edges here. For dihedral group of order 10, so we have 10 elements, and you can see the order of these 10 elements. Identity has order 1, A square, A cube, and A4 has order 5, and B, A square B, A cube B, and A to the 4B has order 2. And you can see here, this is the graph. You know, we don't have edge between, for example, A2 and A3, because A2 has order 5, A3 has order 5 as well. So the common divisor, greatest common divisor of A2 and A3 is 5. They are not co-prime. But A4 and B, they have co-prime, because A4 has order 5 and B has order 2. So you can see here we will have 29 edges. Now, let us give a relation between co-prime degree and co-prime graph. Remember, in my first part of lecture about the probability and group, so the co-prime degree of a graph of a group G is the set of all pairs X and Y, such that X and Y are co-prime. Okay? Divide by order of G square. Now, by this equation, we can write down that order of G square times the co-prime degree is the size of the set of X and Y, such that X and Y are co-prime. Now, we can split this set in two sets. The first set is X, the pairs X and Y, such that X and Y are co-prime order, and X is not equal to 1. X is not equal to Y. right? So x and y are not equal. Union of the set of pairs x and y such that they have coprime order and x is equal to y. So what is this set? If x is not equal to y and x and y are coprime, it means that we will have an H in coprime graph. So we will have an H, and because here we have x, y, and y, x, both are in this set, they have the same H. So the size of this set is the 2 times order of 2 times the number of edges of coprime degree plus, and here the only possibility for x and y which they are coprime and they are equal is that x is identity. So we will have identity E and E, so it's plus 1. Now we will get this formula 2 times the number of edges of coprime graph is order of g square times the coprime degree of g minus 1, or even we can get the number of edges of coprime graph is the half of order of g square times the coprime degree of g minus 1. This is the relation between the number of edges of coprime graph and the coprime degree. Now look at this example. You remember that I proved that the coprime degree of dihedral group of order 8 is 15 over 64. Now, by the above formula, the number of edges of coprime graph, if we put 15 over 64 here, so we will have 1, that's 8 squared, order of 8 squared is 64, 15 over 64 minus 1, so it's 1 over 2 times 15 minus 1, 15 minus 1 is 14, divided by 2 is 7, so the number of edges of coprime graph of dihedral group is 7, and you remember I find the coprime number of edges of coprime graph of dihedral group is exactly 7. So it means that by having the number of edges of coprime graph, we can get the coprime degree, or by having coprime degree of a group, we can find the number of edges. And similarly here, for the number of edges, we find the number of edges for the coprime graph of S3. It was 11, for Z4 we had 3, and for dihedral group of order 10 was 29. Now, by having the number of edges of coprime graph of these groups, we can get the coprime degree. So the coprime degree of S3 is 23 over 60, 36. For Z4 is 7 over 16, and for the dihedral group of order 10 is 59 over 100. We can give some more results about the coprime graph. The first result is that for a finite group G, we can see that the coprime graph is always connected. The diameter is at most 2, and the girth is 3, of course, if we have a cycle. And also, we can prove that the coprime graph is complete graph if and only if the group is a cyclic group of order 2. And also the group G is P group if and only if the coprime graph is a star graph, K1 order of G minus 1. And if G is a non-cyclic group of order P times Q, where P and Q are distinct prime numbers, then the coprime graph of this group is complete tripartite graph. And also we can see that if G1 and G2 are two isomorphism group, then their coprime graphs are isomorphic. But the converse is not true. You can find a counterexample for the converse. Okay. Now let me move to another graph. This is the central graph of a group. You remember I defined the central degree. So suppose that G is a group and the Z of G is the center of group. The central graph of group G we can denote by gamma ZG is a undirected simple graph. The vertex Z is whole elements of G and two elements X and Y, two vertices X and Y, of course distinct vertices X and Y are adjacent if and only if XY is in the center. So as I mentioned here, the vertex Z is the whole elements of the group G, right? And X is adjacent to Y for X not equal to 1. If and only if XY, the multiplication of X and Y is in the center. Now, the important note for the center graph is that we don't have any direction for this graph. You know, the center of a group is a normal subgroup, right? So if X is adjacent to Y, I'm going to show that Y is adjacent to X, so we don't have any direction. If X is adjacent to Y, so it means that by our definition, XY is in the center. And since the center is a normal subgroup, so we can see that X inverse XYX is in the center, but it means that YX is in the center. And here you can conclude that Y is adjacent to X. So we don't have any direction here. So the center graph is an undirected simple graph. You know, we don't have any loop because we assume that X is adjacent to Y by assumption that X is not equal to Y. So X cannot be adjacent to X. So let me give some examples. The first example is that if G is an abelian group, if G is an abelian group, so it means that the center of the group is the whole group. And if we have the center is the whole group, so all vertices are adjacent because we know that the multiplication of any of two elements in a group must be in group. So XY is always in G, which is equal to center. So if G is an abelian group, then the center graph is complete graph. Now, look at S3. For symmetric group of order 6, we have 6 vertices here, right? 6 elements. The center is identity. Now, we have to check that do we have any edge between these 6 vertices or not. You know, identity cannot be adjacent to any other vertices because identity times 1, 2 is 1, 2. 1, 2 is not in the center. 1, 2 cannot be adjacent to 1, 3 because 1, 2 times 1, 3 is 1, 3, 2, but it's not in the center. The only possibility to have H between these vertices is when we have 1, 2, 3 and 1, 3, 2 because 1, 2, 3 and 1, 3, 2 if we multiply, 1, 3, 2 is the inverse of 1, 2, 3. So 1, 2, 3 times 1, 3, 2 is identity, which is in the center. So we will have only one edge here. So the center graph of S3 is K4 bar because 4 isolated vertices, union of 2 and edge which is K2. For dihedral group of order 8, we have 8 vertices, right? We have 8 elements, so we have 8 vertices here. The center consists of 2 elements, identity and A square. Now, here we have edge between identity and A square because E times A square is A square, which is in the center. A times A cubed is identity, is 8 to 4, is identity is in the center. A square B times A square B times B is A square, and it's again in the center. A cube B times AB, it's again because A cube A square is in the center, we can just write A square AB times AB, but AB has order 2, so AB times AB is identity, so A cube B times AB is A square and is in the center. So we will have 4 edges here. So the central graph of the dihedral group is the union of 4 edges, is 4K2. And similarly for quaternion group, we have the same situation for the quaternion group. We will have H because the center of quaternion group of order 8 consists of 2 elements, 1 and minus 1. So we will have an edge between 1 minus 1, I minus I, J minus J, and K minus K. Now, let me give some results about the central graph. The first result is that we have 3 equivalent statements. So G is abelian group, is equivalent to the central graph is complete graph, or the central graph is connected. Now, the second result is very important. For a group G and ZG at the center, we can define 2 sets, X and Y. X consists of all elements of G such that A square is in the center. And Y is the complement of this set, is all elements of G such that A square is not in the center. So the union of X and Y is the all elements of G, so that's the vertex set, right? Now we can give some properties for elements in sets X and Y. The first thing is that there is no edge between any elements in X and any elements in Y. So if X is in X and Y is in Y, then X is not adjacent to Y. If X is in the set X, then we can prove that the degree of X is order of center minus 1. So it means that X is adjacent to order of center minus 1 elements. And if y is in the set y, then the degree of y is exactly the order of center. So it means one more bigger than the previous, the case x in x. And the important result is that this gives the structure of the graph. If G is not abelian, then the central graph has this structure. It's the union of some copies of complete graph and complete bipartite graph, right? So we have order of x times order of zg times of the complete graph k of order of zg, union of some copies of complete bipartite graph k order of zg and order of zg, order of a times 2 times order of zg. So we have some components. So we have some components which are complete graph of order the center, and some complete bipartite component with the size order of center in each parts of complete bipartite graph. Now, how about the relation between centrality degree and central graph? You remember I defined the central degree, the centrality degree for a graph, for a group in my first part of lecture. So the centrality degree, which we denote by pz of g, is 1 over order of g squared times the number of pairs x and y, such that the multiplication of x and y is in the center, right? Now, we can divide this set, the set of x and y, which xy is in the center, into sets, right? So we can split it in two cases. The set of all pairs xy, which x times y is in the center and x is not equal to y, but xy is in the all x and y, which x times y is the center and x is equal to y, right? So the first set gives the edges, the 2 times the number of edges of the central graph, because x is not equal to y and we have x times y is in the center, so we'll have h between x and y. So the first set has order equal to 2 times the number of edges of central graph plus. But how about the second case? We have x and y such that x equal to y and xy is the center. If x is y equal to y, so we'll have x and x. And here xy is x squared is the center. So it's equal to exactly the size of set x, because the number of x such that x squared is the center is the number of x in G, which x squared is the center, and we denote this set by the set x. So here we will have, so the centrality degree is equal to 1 over order of g squared 2 times the number of edges of central graph plus the size of set x. Now, from this equation, we can get the number of edges here. So the number of edges of central graph is the half of order of g square times the centrality degree of g minus the size of x. This is the relation between the centrality degree and the number of edges of central graph. So as example, if we look the symmetric group of order 6, we know that the center of S3 is identity, and previously we computed the centrality degree for S3 was 1/6. Now how about the size of X? X is set of all elements X in S3 such that X squared is the center. Center of S3 is identity, so we have to find all elements X such that X squared is identity. So it consists of identity and 3 elements of order 2. So the size of X is 4. Now by the above formula, the number of edges of central graph of S3 is 1/2 times 6 squared. 6 squared times 1/6 minus 4, which is 1, right? So you can see there, and here I have shown the central graph of S3. We had 4 isolated vertices and only 1 edges. And similarly, for dihedral group of order 8, the centrality degree is 1/4. Now, how about the size of set X? The size of set X consists of all elements of dihedral group of order 8 such that X squared is the center. Center of dihedral group of order 8 consists of identity and A square, right? So we will have identity, because identity, the identity square is identity, A square is A square, it's in the center, A square is A to the 4th identity in the center, A cube square is A to the 6th is A square, again in the center, B square is identity, AB square, A2 B square, and A cube B square, that's all elements of order 2, and the A square is identity. So the X consists of all elements of the dihedral group, so the size of X is 8. Now the number of edges is 1/2, 64 times, that's the centrality degree, is 1/4 minus 8 is 4. And here is the central graph. We have 4 edges here. So by having the centrality degree, we can find the number of edges for the central graph. And conversely, if we have the number of edges for any number of edges of central graph for any group, we can easily find the centrality degree for that group. Okay, now the last graph which I would like to introduce here is a bipartite graph associated to a group, which means that we are going to introduce a graph associated to some elements and some automorphism of a group. Let me give a definition. So Suppose that G is a group and ZG is the center of the group G. So you remember again in my first part of lecture, I introduced the automorphism group. So automorphism group of G, we denote by auth of G. Automorphism group is a homomorphism from G to G such that this homomorphism is 1-to-1 and onto, so it's an isomorphism. We call it homomorphism. So you remember I defined two subgroups. LGZG is the set of all elements of G in G such that G inverse alpha of G is in the center for all alpha is inter automorphism group. And auth CG, which I call this subgroup by central automorphism, right, is the alpha in automorphism group G such that G inverse alpha G is in the center for all G in G. So as I have already mentioned, the first one, LGZG, is a subgroup of G, and auth CG is a subgroup of automorphism group of G. Now, by knowing these two subgroups, I'm going to define a graph. Put A as the group G minus LGZG. LGZG is a subgroup. So G minus it's this subgroup. B is automorphism group G minus the central automorphism of G. This is a subgroup. So A and B are this, consider these two sets, and I'm going to define a bipartite graph. So the two parts of vertex set of this graph consists of these sets A and B. So the vertex set is the union of A and B. Now, if we have two vertices, so G in set A, right? A is some elements of A and B is some automorphism. So if G is in A and alpha in B, so G is an element and alpha is an automorphism, we can say that G is adjacent to alpha if and only if we have this condition: G inverse alpha of G is not in the center. G inverse alpha of G is not in the center. So here, so this is the bipartite graph. The first part is A, set A, which is G minus LGZG, and the second part is automorphism group G minus the central automorphism. So if you take element G as a vertex in the first part and alpha is an automorphism in the second part, G is adjacent to alpha if and only if we have this condition: G inverse alpha G is not in the center. This is a bipartite graph. Now, look at this example. If we take S3 as a symmetric group of order 6, right? We have 6 elements here. The center of S3 is trivial subgroup identity. So for the automorphism, group of S3 consists of 6 automorphisms. I determine this 6 automorphism. For example, automorphism alpha 1, take any of these 6 elements to itself, so alpha 1 is the identity. Alpha 2, take identity to identity, 1 2 to 1 2 2 3, 1 3 to 1 3, 2 3 to 1 2. So 1 2 3, 1 3 2, and 1 3, they are fixed. You know, we have 6 automorphism here. So how about the central automorphism? The central automorphism of group S3 consists of all automorphism like alpha, such that G inverse alpha G is in the center for all G in S3. So G, because the center of S3 is trivial, so G inverse alpha G is identity. It means that alpha G is G, so alpha fixed G, right? So the central automorphism of G consists of all automorphism such that automorphism fix all elements of S3. So alpha G is G for all G is in 3. The only automorphism which fix all elements of G is the identity automorphism. So it's alpha 1. So the central automorphism of G is alpha 1. How about LGZG? LGZG is the set of all elements G in S3 such that G inverse alpha G is element in the center. The center is trivial. So again, this all element G in S3 such that alpha G is G for all alpha in automorphism G. So we have to find all elements of G that fixed by all automorphism. So all automorphism, we know that fixed identity elements. So the LGZG is E. Now, the vertex set. The vertex set of this graph is union of two sets A and B. How about A? A is S3 minus LS3Z S3. Union of, and set B is the automorphism group of S3 minus the central automorphism of S3. So we have 5 elements here because we have to remove identity from the first part, right, from S3. And here again 5 automorphism because we have to remove alpha 1 as the identity automorphism, right? So we have 5 elements in the first part and 5 automorphism in the second part. Now this is the graph. You know, for example, alpha 2 here adjacent to all 5 vertices here. But for example, alpha 5 can only adjacent to 1, 2, 1, 3, 2, 3. Alpha 5 cannot adjacent to 1, 3 or 1, 3, 2 because, you know, 1, 2, 3 cannot be adjacent to alpha 1 because alpha 5. Alpha 5 of 1, 2, 3 is 1, 2, 3. So alpha 5 fixed. We know that when 1, 2, 3 adjacent to alpha 5, if and only if alpha 5 of 1, 2, 3 is not fixed, but here is fixed, right? And similarly 1, 3, 2 is not adjacent to alpha 6 because alpha 6 fixed, again 1, 3, 2. But 1, 2 adjacent to alpha 2 because alpha 2 of 1, 2 is 2, 3, which is not equal to 1, 2. So cannot fix 1, 2, so we will have adjacent. Now, we can give some results about this graph. The first result is that we don't have any isolated vertices. If G is abelian group, then the graph is null graph. We don't have any edges and here and vertices. So in the edges, if G is a non-abelian group, then the girth is 4, and also if G is a vertex in the first part and alpha is a vertex in the second part, they are lower bound for the degree of alpha and degree of G. The diameter is at most 4. If the part A and B, they have the same size, then we can say that the graph is Hamiltonian. The independence number, which is the maximum size of independent set, is the maximum size of the first and the second part. And if the size of central automorphism and the size of LGZG is at least 3, then the graph is not planar. Now, look at the relation between the centrality, the central automorphism degree, which I defined, and this graph. The central automorphism degree of alpha in G, as I defined before, is the 1 over the order of G times the number of elements G in G, such that G inverse alpha G is in the center. Alpha is a fixed automorphism, right? Now, look at here. We know that G is the set of all elements in G such that G inverse alpha G is in the center, union of all G in G such that G inverse alpha G is not in the center. So we can write down this order of G is, but this one, G in G such that G inverse alpha G is in the center. This is the the order of G times the central automorphism degree of alpha. So that's order of G P alpha of G plus, and that one is the set of all G in G such that G inverse alpha G is not in the center. You know, if G has this property, G in G, such that G inverse alpha G is in the center, it means that G is adjacent to alpha. So the size of the set G in G, such that G inverse alpha G is not in the center, is the degree of alpha, right? So that's all elements in the first part which are adjacent to alpha. So this order of G, P alpha of G plus degree of alpha. So we can write down the central automorphism degree of G, P alpha of G, is 1 minus 1 over order of G, the degree of alpha. So as example for S3, so the degree of elements, you know, degree of 1, 2, 1, 3, 2, 3 is 4, degree of 1, 2, 3, 1, 3, 2 is 3, and degree of automorphism alpha 2, alpha 3, and alpha 4 is 4, and degree of alpha 5, alpha 6 is 3. So by this information, which I can get from the graph, you know, the degree I found here, the degree of alpha 2 here, you can have alpha 2, alpha 3. So by this information we can get the just central automorphism degree for each automorphism. Okay, so what I have done in the second part of my lecture is to give some relations between probability, between graph, and of course probability and graph are defined for the group. So I explained some example about these three important concepts: group, probability, and graphs. I do not have enough time to mention more about such graphs, but there are many graphs in this area, and you can just follow even these graphs because there are many problems, many questions, many open problems and research problems for these graphs, and we can just consider in some different view of points. We can consider through the probability or through the graph or together. So we can put, for example, assume that you have a fixed amount of probability. So what we can say about the construction, structure of group, what we can say about the graph related to group. Otherwise, if you have a class of groups, what you can say about the probability, about the graph, we have many problems. So in this part, unfortunately, there is no time for answer question. So I prefer to have just answering your questions and just hearing your comments in the third part of my lecture, which I will combine matrix. Thank you very much, and sorry for taking your time. So I hope to just organize all my topics in this series of lectures in the third part of my lecture. Thank you very much indeed.
Okay, it is getting more interesting. Let us give an applause for Professor Erfanian. Unfortunately, because we don't have too much time for the Q&A session, maybe I will let for just one question, if any. You can use, okay. Okay, Ran, it's there are three questions, but maybe for this session, I will read Rangga Nugraha's question first. Have you considered to construct some graphs from a semigroup, Professor?
Actually, we may define graphs related not only semigroup to algebraic structures, right? So this sort of graphs actually called algebraic graphs. So we may define a graph related to a ring, to a module, to a semi-ring, to semigroup, to monoid, to everything. It depends on defining the graph. So because when you want to define a graph, you have to make sure that the graph is not so easy. It means that everything is clear, or is not so difficult. So it's very important. If the graph is very difficult, so you cannot able to find anything, and it is not interesting. So the definition of graph is very important. So if you define a very good graph means that a graph which you can able to find some properties, not too easy, with some more calculations, some more just some rules, some more theorems you can use. And also the motivation is important, to give a motivation for defining a graph. So if you want to define a graph, you have to see that what's your motivation for this graph. So it's very important. Yes, we have many graphs related to semigroup. For example, one of important graph in related to a group or even in semigroup is a Cayley graph. So we have a generalization of Cayley graph for a semigroup. Yes, we have some graphs related to, hopefully for the next time, I may mention a series of lectures about the graphs or probability related to some other algebraic structures like ring, module, semi-ring, and so on, not only group.
Okay, thank you so much, Professor Erfanian. And maybe I think we have 5 minutes left before the break. So I will read one more question from I'm sorry, Wahid Fitri Albar. The question is, how did you find the inspirations to define those graphs by those ways? I found that the results by connecting each other concepts are magnificent. That's the question.
Well, you know, it's important to see that how you want to define a graph, and because if you want to define a graph, we have many topics in graph. So in the third part of my lecture, I will talk about some matrices related to graph. So for some, okay. I think, all right. Okay, so it's important to see that. So if you want to define a graph, so what you are going to investigate about what kind of properties of graph. So the matrix related to graphs is one of important topics, and we have many applications about the matrix, because we can find some numerical analysis or something like that, right? So it's up to you to see that why you are going to define a graph and what's your motivation for a graph.
Okay, thank you so much, Professor Erfanian. And then I think we have 2 minutes left if it is enough to answer the last question from UD. Dear Professor, we know that every graph corresponds to their adjacency matrix. From your presentation, we see that a finite group can induce many adjacency matrices. Is there any results obtained so far related to the eigenvalues and eigenvectors of those matrices?
Okay, so that's the topics which I will talk about these properties in my third part of lecture, about the adjacency matrix and Laplacian matrix. So that's very interesting question, and I will just explain in my last part of lecture this afternoon.
Okay, so we will see it in the last part of Professor Erfanian's lecture.
Thank you very much.
Thank you very much, Professor. So that's all for our Q&A session for this second session. Thank you so much again for Professor Erfanian and also for all of you, all participants.
Okay,
Oh.
thank you very much.
Okay, before we continue to the last part of Professor Erfanian's talk, there is a coffee break for 20 minutes. So we will be back again here at 15:30 or 15:25, of course, in GMT +7. So let's take your break and see you.
Okay, so it's not real coffee break, it's the virtual coffee break.
Virtually coffee break.
Okay, thank you very much indeed.
Thank you so much.
Okay, see you
So,
this afternoon.
Okay, ladies and gentlemen, we will back to the next session. So please get back to your seat, turn on your camera, be focused again, and of course, take your note.
Okay, so it's the last part of my talk on 4 concepts, groups, probability, graphs, and matrices. In the first lecture this morning, I introduced some probabilities associated to some groups, and in the second part of my lecture, I introduced some graphs associated to a group and state some relations between the probability and graph. As you remember, I find a formula between the number of edges of a given graph and the probability which I introduced. Now, I'm going to mention one more concept, which is a matrix. Matrix is a concept which is very important in not only in algebra, but also in analysis, in geometry, and so on. So I'm going to state some matrices associated to a graph, and then finally give some relations between matrices, graphs, and probability for a given group. Now, first of all, I need to define and remind some matrices associated to a graph. We have many matrices which are associated to a graph. But I'm going to introduce just few of them. I will introduce and define 4 of important matrices for a given graph. Right. The first matrix for associated to a graph is called incidence matrix. So let me define the incidence matrix. You know, just let me give a just note that some of matrices are defined for directed graph and some of them for undirected graph. The incidence matrix is a matrix which is associated to a directed graph. You know, we are talking about here for this matrix is directed simple graph. Right. Suppose that gamma is a directed simple graph, and the vertex set of graph gamma we can denote by 1 to n. So we have n vertices, and we may denote the H set, the E of gamma, by the set of edges E1, E2, and En. So the graph gamma has n vertices and m edges. The incidence matrix of gamma that we can denote by Q of gamma is n times m matrices, and n times m matrix, which the rows and columns of this matrix are indexed by the vertex set and edge set, respectively. So it means that we have n rows and m columns because we have n vertices and m edges. The ij entry of incidence matrix is defined 0 if vertex I is not belong to H, E, and this E sub EJ, right? Because EJ has two, EJ is an H, and we have two vertices for this H. If each of, not each of this, not initial vertex and not terminal vertex of EJ is not I, or equivalently we can say that I is not belongs to the HEJ. In this case, the IJ entry is 0, right? And otherwise, we have two cases. So if I is the originate vertex of HEJ, it means that we have a direction for EJ, right? For example, EJ, maybe we can denote vertices of EJ by X and Y. So EJ is an H from vertex X to Y, right? So X is the initial vertex or originate vertex, and Y is the terminate. So if I is belongs to HEJ, and if I is the initial vertex, we can put 1, and if I is the end vertex of EJ, we may put -1, right? Let me give an example to just see the inside this matrix. Suppose that gamma is the following graph. So you can see it is a directed graph, right? We have 5 vertices here, and we have 6 edges. So we denote the vertex set as the set of 5 vertices, 1, 2, 3, 4, 5, and we have 6 edges, E1, E2, E3, E4, E5, and E6. Now look at here. The first row. Now vertex 1, is that vertex 1 belongs to HE1? Yes, vertex 1 is on HE1. Now vertex 1 is the beginning or end is the initial or terminate is end. So since 1 is on HE1 and it's the end vertex of E1 according to the direction, so we can put -1. How about E2? 1 is also belongs to HE2, but for the HE2 we can see that 1 is the initial vertex of E2, so we can put 1. For E3, 1 is also belongs to HE3, but 1 is the end vertex of E3, so we put -1. Now E4, you can see that 1 is not belongs to E4 because the vertices of E4 is 2 and 5, so we put 0. And similarly, 1 is not on the HE6, right? Because A6 consists of vertices 5 and 4, so again is 0. So we can just put all entries according to this rule. We can also fill this matrix as an easier way. Look at here. So if you take the first column belongs to HE1. We can see that E1 has two vertices, 2 and 1. 2 is the initial and 1 is the terminate. So E1 is 2 to 1, so we can put for E1, the first column 2, we can put 1, and for 1 is -1, and the other entries in this column is 0. The second column belongs to E2. E2 consists of 2 vertices, 1 and 3. So E2 is an H from 1 to 3. So you can see that here we put 1 for the first row and -1 for the third one. So we can just column by column fill an easier way to complete the inside this matrix of gamma. So you can see that the inside this matrix of gamma is 5 times 6 matrix because we have 5 vertices and 6 edges. Right. One of important topics on the inside this matrix is the rank of matrix. Rank of inside this matrix. You know the definition of the rank of a matrix. If we have n times m matrix A, so the rank of matrix A, which we can denote by rank of A, is the number of independent rows, which is equal to the number of independent columns. Or we can say that the dimension of row space or column space, which are equal. Now, let me give an example of a disconnected graph. Suppose that we have 5 vertices, 1, 2, 3, 4, 5. So we have an edge from 2 to 1, and here we have 3 to 4, 5 to 4, and 3 to 5. So we have 5 vertices and 4 edges. the inside this matrix, if you look here, for the first column E1, we have H from 2 to 1, so here is 1 and minus 1. E2 is from 3 to 4, so we have just opposite of row 3 is 1, and for row 4 is minus 1. And similarly, E3 is from 3 to 5, so it's 3, 1, 5 is minus 1, and E4 is 5 to 4, so we have in row 5 is 1, and in row 4 is minus 1. Now, what's the rank of inside this matrix of graph X and also the graph gamma here? Here you can easily find that the number of independent rows is 4, so the rank is 4, and for the inside this matrix of X, the rank is 3. Now, there is a very nice theorem about the rank of inside this matrix, which says that for a given gamma, graph gamma with n vertices, if gamma is a connected graph, then the rank is n minus 1. We have n vertices, so it doesn't matter how many edges we have. If the graph is connected and has n vertices, the rank of inside this matrix is n minus 1. And if gamma is not connected, and if it has n vertices and k connected components, then the rank of inside this matrix of this graph is n minus k. So you can see that if the graph is connected, so it means that we have only one component, so you can get n minus 1 as before. Right. In a special case that the graph is a tree, so if gamma is a tree, of course directed tree with n vertices, so you know that the rank of this graph, because the tree is connected and has n vertices, the rank is n minus 1. Now, the size of inside this matrix is n times n minus 1, because in a tree we have n vertices and we have n minus 1 edges. So the inside this matrix of a tree is n times n minus 1. Now, it's easy to prove that every square n minus 1 times n minus 1 submatrix of the inside this matrix of gamma, of 3 gamma, is non-singular. It means that it's invertible. For example, let T be a following tree, which is the path, right? So we have 5 vertices and we have 4 edges. So the inside this matrix of T of graph of path T is 5 times 4 matrix, and you can see that's the entries of the inside this matrix. For example, look at the first column, E1. E1 is from 1 to 2, so we have 1 and minus 1. E2 from 2 to 3, we have 1 minus 1. E3 is from 3 to 4, so we have 1 minus 1, and E4 is from 4 to 5. So we have 1 minus 1 here, and other integers are 0. So the rank of inside this matrix of this path is 5 minus 1. 5 is the number of vertices, is 4. So it means that the rank is 4. So if we remove any just any row, for example, the last row or the row 4, 3. So if we remove one row, then we can get 4 by 4 matrix, and by the above theorem, it's non-singular or it's invertible. So, you know, these are some 4 times 4 submatrices of the inside this matrix of 3T. Right. Now let me move to the another matrix for a given graph. The second matrix called 0, 1 inside this matrix. That's a special case of inside this matrix, which is not necessary for a graph gamma to be directed. So let gamma be a graph not necessarily directed, and if we have the vertex set of gamma is the set of 1 to up to n, and the edge set is E1, E2, and En, right? Now, the 0, 1 inside this matrix of gamma, we can denote by M of gamma, is again n times M matrix, but the entries defined as you can see. So if take vertex I and H, E, J. So if I is not belongs to H, E, J, we will have 0. Otherwise, if I is one of vertices, one of two vertices of H, E, J, it doesn't matter is the initial or terminate. In both cases, we can put 1. In other words, so the difference of inside this matrix and 0, 1 inside this matrix is that we may put, we may replace -1 to 1 inside this matrix. For example, for complete graph of order 4 or K4, we have 4 vertices and we have 6 edges. You know, any of 2 vertices in K4 are adjacent. So the 0, 1 inside this matrix, you can see here, right? So look at first column, E1. For E1, E1 is from 1, between 1 and 4. So we can put 1 here, and just for the row 4 is again 1. E2 is between 2 vertices 1 and 2. So the first and the second row is 1 and 1. And similarly, you can fill all other columns. So one of important property of inside this matrix is that in the case of we have a cycle of length n, for n is bigger than or equal to 3. So if you look the 0, 1 inside this matrix of cycle Cn, then we have 2 cases for the determinant of this matrix, because you know the inside this matrix of Cn is a square matrix because we have n vertices and we have n edges. So we can just ask about the non-singularity. So here you can see that if n is even, so the determinant is 0, so it means that the inside the 0, 1 inside this matrix of C1 is not non-singular, it's singular. And if n is odd, then the determinant is not 0, it's 2, and the inside the 0, 1 inside this matrix of C1 is invertible. And also, it's a theorem to say that if gamma is a connected graph with n vertices, then depending on gamma is bipartite or is not bipartite graph, then the rank of 0, 1 inside this matrix is n minus 1, right? Here is when gamma is bipartite. So in this case, the rank of 0, 1 inside this matrix and the rank of inside this matrix are the same, it's n minus 1. But if the graph gamma is not bipartite, so the rank of 0, 1 inside this matrix is n. For example, so if you look the complete graph, so if n is 2, it's bipartite, so the rank is n minus 1 is 1. But for n is bigger than or equal to 3, so the complete graph Kn is not bipartite, so the rank of 0, 1 inside this matrix is n. And similarly for 0, 1 inside this matrix of C4, because C4 is bipartite graph, so the rank of 0, 1 inside this matrix is 3. All right. Now, let me define the third adjacency, the third matrix for a given graph, which is adjacency matrix. Adjacency matrix is one of very, very important matrix associated to a graph. So let me define the adjacency matrix for the graph gamma. So suppose that gamma is a graph with n vertices, so the vertex set is 1 to n, and we have m edges, so it's the set of E1, E2, and EM. The adjacency matrix of gamma, that we can denote it by A of gamma, is a square matrix, is n times n matrix, whose rows and columns are indexed by the vertex set. You know, inside this matrix, it was not necessary to be a square, because the number of vertices and the number of edges are not necessary to be the same. But here, you know, columns and rows both are indexed by the vertex set. So the adjacency matrix is always a square matrix. So it's n times n matrix. Now, how about the definition of entries of adjacency matrix? So if I and j are two vertices, right? If I is not equal to j, so the ij intra of adjacency matrix of gamma, we have two cases. We put 0 if I is not adjacent to j, and we will put 1 if I is adjacent to j. And if I and j are equal, then the entries on the diagonal are 0. So you can see that. So the adjacency matrix of graph gamma is a square matrix, is n times n matrix, and if the entry I, j, if we denote by a small a, aij, then if I is j is 0, so it means that all entries on the diagonal is 0. If I is not equal to j, if I and j are distinct, so we have two cases. If I is adjacent to j, we will put 1, and if I is not adjacent to j, the entry is 0. Right. Let me give example again. Suppose that the graph gamma is the graph consists of 5 vertices, right? And we have 1, 2, 3, 4, 5, 6, 7 edges. It doesn't matter how many edges, because the adjacency matrix, the size of adjacency matrix is dependent only the size of vertex set. So we have 5 vertices. So the adjacency matrix is 5 times 5 matrix. Now how about the entry? 1 and 1 is 0. 1 and 2, we have an edge between 1 and 2, so we can put 1. 1 and 3. 1 and 3, we have an edge, so it's 1. 1 and 4. 1 and 4, again we have an edge, is 1. 1 and 5, we don't have edge between 1 and 5, so it's 0. The second row, so 2 and 1, we have an edge, is 1. 2 and 2 is 0. On the diagonal, as I mentioned, it's always 0. So 2, 3, we have an edge. 2, 3 is 1. 2, 4, there is no edge, so it's 0. 2, 5, there is no edge, so it's 0. So you can see that's the adjacency matrix of graph gamma. If we consider the path Pn, right? So we have n vertices. So the adjacency matrix of the path Pn is n times n matrix. So on the diagonal we have 0. So just the one shift after diagonal, that's all 1, and one shift before, just below, so one row diagonal, just below and upper of the diagonal is 1, because we have between 1 and 2 we have h, so here we have 1, and also here 2, 1. We have 2, 3, 2, 3, yes, 2, 3, and 3, 2 is here. So that's the adjacency matrix of a path. And similarly for the complete graph. For the complete graph, we have only 0 on the diagonal, and other entries are all 1, because we have an edge between any of two vertices. If I and j are two different vertices, we will have an edge, and we will have a just entry 1. Now, one of important subject related to adjacency matrix is the energy of a graph. Energy of a graph actually coming from the eigenvalues of the adjacency matrix. Let me define the energy. So suppose that gamma is a graph with vertex set consists of vertices 1 to n and H set E1, E2, En. So if A of gamma is the adjacency matrix of gamma, so you know A gamma is n times n matrix. And you know, because A adjacency matrix is symmetric, so we will have real eigenvalues. So we will have n real eigenvalues. So if lambda 1, lambda 2, and lambda n are all eigenvalues of the adjacency matrix, then the energy of the graph gamma, which we can denote by just E of gamma, is the sum of absolute values of all eigenvalues of the adjacency matrix. In other words, the energy of gamma is the sum of absolute values of lambda I, where I is 1 to n. Actually, the energy of a graph just originally comes from the chemistry, and there is a motivation for of chemistry for the energy, right? Okay, as an example, suppose that K23 is a complete bipartite graph. So we have two vertices in the first part, 1, 2, and 3 vertices in the second part, 3, 4, and 5. And you know, 1 is adjacent to 3, to 4, to 5, and 2 is adjacent to 3, 4, and 5. So that's a complete bipartite graph. So how about the adjacency matrix? So adjacency matrix of K2, 3, here you can see between 1, 1, 1, and 2, because the first part, 1 and 2, is an independent set, so we don't have any H, so both are 0. And similarly, between 3, 4, and 5, there is no H, and the entries are 0. But if you take between 1, 2, and 3, 4, 5, we will have an H between any of 1, 2, and 3, 4, 5. So we will have all entries are 1 here. So you can see that's the adjacency matrix of K23. Now, if we compute the eigenvalues of the adjacency matrix of K23, right? So we will have 3 eigenvalues 0. So it means that we have 0 with the multiplicity 3, and we have 2 more non-zero eigenvalues, which is minus square root 6 and square root 6. So what's the energy? The energy of complete bipartite graph K23 is the summation of absolute value of this eigenvalues, and is 2 times the square root of 6. We have many results about the energy, and just some relations between energy and other topological invariant of a graph. So this is only one of results, which is the just lower bound for the chromatic number. So if gamma is a graph with n vertices and at least one edge, so if lambda 1 of gamma is the biggest eigenvalues and lambda n of gamma is the smallest eigenvalues of the adjacency matrix of gamma, then we will have an upper and we will have a lower bound, which is 1 minus lambda 1 of gamma over lambda n of gamma. It's a lower bound for the chromatic number of gamma. And also, it's interesting to see that if we compute the energy of a graph, so if the energy of graph is a rational number, in this case it must be an even integer. So we have two cases. If the energy of gamma is rational, so it doesn't matter, but if it's rational, so it must be integer and even. Okay, now let me introduce the number 4 of matrix, which is Laplacian matrix for a graph. Suppose that gamma is a graph, the vertex set is the set of 1, 2, up to n, and the edge set is E1, E2, En. So we have n vertices and m edges. The Laplacian matrix of gamma, we may denote it by L of gamma, is again just similar to adjacency matrix, is a square matrix, is n times n matrix. So the rows are and columns are of Laplacian matrix are indexed by the vertex set, right? Now we have, let me just define the Laplacian matrix. So as you can see here, the rows and columns are indexed by vertices. So we have 1, 2 up to n and 1, 2. So if take vertex I and vertex j, so the entries Lij, right? We have three cases. The first case, if I is equal to j, so it means that the diagonal of Laplacian matrix. So if I equal to j, the entries I and I is the degree of I. Degree I means the number of vertices which are adjacent to vertex I, right? So if I is j, the Lii is the degree of I. Now if I is not equal to j, now we have two cases. If I is adjacent to j, we will put -1, and if I is not equal to j, we will put 0. So the matrix consists of 0, -1, and on the diagonal we have some integers which are the degree of vertices. Now look at this example. So suppose that gamma is the following graph. We have 6 vertices and some edges, 1, 2, 3, 4, 5, 6, 7, 8 edges. Now first of all, let me compute the degree of any vertex. The degree of vertex 1 is 3. We have 3 edges, right? Degree of 2 is 3. Degree of 3 is 2. Degree of 4 is again 2. Degree of 5 is 5. And degree of 6 is 1. Now, the Laplacian matrix of graph gamma, as you can see, I put on the diagonal these degrees. So we have 3, 3, 2, 2, 5, 1. Depending on here, the degree of 1 is 3, 3, 2, 2, 5, 1. So that's the diagonal. Now, how about other entries? So look at here, 1, 2. 1, 2, 1 is adjacent to 2, right? Because we have an edge between 1 and 2. Since we have an edge between 1 and 2, so it's -1. Now, 1, 3. 1, 3, we don't have edge between 1 and 3, so it's 0. Right? Again, 1, 4, we have an edge between 1 and 4, so it's -1. 1, 5, we will have edge between 1 and 5, it's -1, right? And 1, 6, there is no edge between 1 and 6 is 0. So, you can just fill the other intervals by the same way. That's the Laplacian matrix of this graph. It's easy to see that the Laplacian matrix of complete graph, in complete graph, the degree of any vertex is n-1 because any vertex is adjacent to all other vertices. So on the diagonal, we have n-1, and other entries are all -1. Because if you take any two vertices, I and j, which I is not equal to j, we will have an edge between I and j, so it's -1. So the Laplacian matrix of a complete graph Kn, we have n-1 on the diagonal, and other entries are -1. Now, the similar as the energy which I defined for the adjacency matrix, now we can define the Laplacian energy for the given graph. Let me define it. Suppose that gamma is a graph with n vertices, and if L of gamma is the Laplacian matrix of gamma. L of gamma is n times n square matrix. And by definition of Laplacian matrix, you can see that, again, the Laplacian matrix is a symmetric matrix, and so all eigenvalues of Laplacian matrix are real, so we will have n eigenvalues. If mu1, mu2, and mun are all eigenvalues of the Laplacian matrix of gamma, then the Laplacian energy of gamma, we may denote by Le of gamma, is defined as the summation is the sum of absolute values of all eigenvalues of the Laplacian matrix. So Le of gamma is sum of I from 1 to n absolute values of mu I. Now, as an example, look at the past P tree. We have 3 vertices, 1, 2, 3. So the Laplacian matrix of P tree is, the degree of 1 is 1, degree of 2 is 2, degree of 3 is 1. So the Laplacian matrix on the diagonal, we have 1, 2, 1. Now, other entries, we have between 1 and 2, we have an edge, so we will have -1. 1 and 3, there is no edge, so it's 0. 2 and 1, we have -1. So 2 and 2 is the degree of 2 is 2. And 2 and 3, we have an h between 2 and 3, so it's -1. 3, 1, there is no h, is 0. 3, 2, we have an h is -1. And 3, 3 is on the diagonal, is the degree of 3 is 1. That's the Laplacian matrix of P3. Now, how about the eigenvalues? Eigenvalues of P3. So if we compute the characteristic polynomial for the Laplacian matrix, so the characteristic polynomial f of x is the determinant of xi minus the Laplacian of P3. So it's the determinant of this matrix, it's 3 by 3, and it's equal to x times x minus 1 times x minus 3. So we have 3 eigenvalues. Lambda 1 is 0, lambda 2 is 1, and lambda 3 is 3. So the Laplacian energy of P3 is 0 plus 1 plus 3 is 4. Okay, so we have some more matrices, but unfortunately we don't have more time to introduce all of them. So maybe that's enough for our purpose of give a connection between these matrices, graphs, probability, and groups. Okay, so I will move to the just graph related to group and find some of these matrices and give a relation between the probability Okay, now we are going to give 2 examples and use these matrices and probability, so all together. Look at example 1. Suppose that the dihedral group of order 8 is D8, right? So I have given some questions. The first one is that consider non-commuting graph of D8. So draw this graph, draw the non-commuting graph. Second is the commutativity degree of the dihedral group of order 8. The third part is how about the adjacency matrix, how much is what's the value of energy, and the same for Laplacian matrix and Laplacian energy, and finally find some relations between commutativity degree, adjacency matrix, and Laplacian matrix. Okay. Now, let me give solution for each part. As you know, the dihedral group of order 8 has 8 elements, right? So we have identity A square, A cube, B, AB, A cube B, A square B, and A cube B. The center of dihedral group consists of 2 elements, identity and A square. So the vertex set of non-commuting graph consists of 6 elements. So we removed identity and A square from the set of elements of D8. So the vertex set consists of A cube, B, AB, A cube B, A square B, and A cube B. And here you can see the non-commuting graph, which I have already mentioned in the second part of my lecture. You know, A is adjacent to B, A square B, A cube B, AB, right? But A cannot be adjacent to A cubed. Okay, we have 12 edges here. The second part is the commutativity degree of the 8. So, as I mentioned in the first part of my lecture, the commutativity degree of dihedral group of order 8 is 5/8. Okay. Now, how about the adjacency matrix? Look at here. The adjacency matrix of non-commuting graph of D8 is 6×6 matrix because we have 6 vertices. So the adjacency matrix is 6×6, right? Here you can see A cannot be adjacent to A, so here is 0. A also cannot be adjacent to A cube because A and A cube commute, so it's 0. But A is adjacent to B, also AB, A square B, and A cube B. So you can see the values of the adjacency matrix of non-commuting graph of D8. How about the eigenvalues? So if we compute the eigenvalues of this adjacency matrix, this 6×6 matrix, so the eigenvalues are, we have 0 of multiplicity 3 and also -2 of multiplicity 2 and 4. So how about the energy? The energy of non-commuting graph is the sum of absolute value of all eigenvalues. So we will have 0 plus 2 plus 2 plus 4, right? And it's 8. So the energy of non-commuting graph of dihedral group of order 8 is 8. What we can say about the Laplacian matrix? As you know, on the diagonal of Laplacian matrix, right, we have to put the degree of vertices. So the degree of A A cube B, AB, A cube B, A square B, and A cube B, they are all 4, right? So we have 4 on the diagonal, and you can see A is not adjacent to A3, so we have 0. A is adjacent to B, we have -1. A is adjacent to AB, we have again -1. A is adjacent to A square B, we have -1, and A is adjacent to A cube B is -1. And with the same calculation, we can complete all entries of the Laplacian matrix of non-commuting graph of D8. Now, the eigenvalues of the Laplacian matrix of non-commuting graph of D8, we have 6 eigenvalues. It is 0, we have 4, 0 of multiplicity 1, 4 of the multiplicity 3, and 6 of the multiplicity 2. So the Laplacian energy is the sum of these numbers and is 24. Now, the important thing is to find some relations between non-commuting graph, commutativity degree, and Laplacian matrix, adjacency matrix all together. You know the relation between the number of edges of non-commuting graph and the commutativity degree of D8. So the number of edges is the half of order of D8 squared times 1 minus the commutativity degree of D8. Now, look at the adjacency matrix. If we put the adjacency matrix of non-commuting graph by Aij, the entries, so what's the summation of all entries? The summation of all entries of the adjacency matrix, right, is the 2 times of the number of edges, right? Because if you look every entry, the number of ones for each row is the degree of that vertex. So the summation of all entries is the sum of all degree of vertices, and that's the 2 times of the number of edges. So we will get the formula between the number of edges and the sum of all entries of the adjacency matrix. So it's half of the sum of all entries of the adjacency matrix. Or we can say the sum of all entries of the adjacency matrix is order of the group order of D8 squared times 1 minus the commutativity degree. And as you know, the diagonal of Laplacian matrix is the degree of vertices. So what's the summation of all entries on the diagonal? Again, it's the summation of degree of all vertices, and it's again 2 times of the number of edges. So we will get another 2 formulas for the number of edges in terms of the summation of all entries on the diagonal of Laplacian matrix. And the same thing, this is the relation between the sum of all entries on the diagonal of Laplacian matrix and the commutativity degree. So it means that by having the commutativity degree, we can find this summation, and if we have the Laplacian matrix, we can find the commutativity degree. So, we can just transfer each of them to other one. Now, the second example is the symmetric group S3 and co-prime graph. So, if S3 is the symmetric group on 3 letters, right? So we will have 6 elements: identity, 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. Now, the first part is to draw co-prime graph of S3. The second part is the determining co-prime degree of S3. The third part is the adjacency matrix of co-prime graph of S3, and also the energy of co-prime degree of S3, Laplacian matrix of this graph, Laplacian energy, and again find some relation between co-prime degree, co-prime graph, and adjacency matrix and Laplacian matrix. The first part is to draw the co-prime graph of S3. So as you can see, that's the elements of S3, and that's the orders of elements of S3. So you can see identity element will adjacent to all other elements, and 1, 2, 1, 3, and 2, 3 adjacent to identity, 1, 2, 3, and 1, 3, 2. Right? So there is no edge between 1, 2, and 1, 3, and 1, 3, 1, 2, because they have the same order and they are not co-prime. So this is the co-prime graph of S3, and we will have 11 edges. As I have already computed in the second part of my lecture, the co-prime degree of S3 is 23 over 36. Now, here is the adjacency matrix of co-prime graph of S3. You can see in the first row, identity cannot be adjacent to itself, but identity is adjacent to 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. So we have 1 for each of them. 1, 2 is adjacent to identity, but it's not adjacent to 1, 2, 1, 3, and 2, 3. So we have 3 zeros, but 1, 2 is adjacent to 1, 2, 3, and 1, 3, 2. So we have 2 ones. So the same computation, we can fill the adjacency matrix. The eigenvalues of the adjacency matrix of co-prime graph, we have 0 of multiplicity 3, and we have 3 more eigenvalues, minus 2.271, minus 1.341, and 3.612. So the energy of co-prime graph is 7.224. The Laplacian matrix of coprime graph of S3, it's here, on the diagonal, the degree of identity is 5, the degree of 1, 2, 1, 3, 2, 3 is 3, and the degree of 1, 2, 3 and 1, 3, 2 is 4. So we have 5, 3, 3, 3, 4, and 4 on the diagonal. So on the first row, you can see that identity is adjacent to 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. So we have to put -1 for each of them. Here, look at the row 4. Here, 2, 3 is not adjacent to 1, 2, so we have 0. 2, 3 is not adjacent to 1, 3, again we have 0. But 2, 3 is adjacent to 1, 2, 3, we have to put -1. The eigenvalues of the Laplacian matrix of coprime graph of S3 are, we have 6 eigenvalues, so we have 0, we have 0 of multiplicity 1, 3 of multiplicity 2, 4 of multiplicity 1, and 6 of multiplicity 2. So the Laplacian energy of this graph is 22. So by the same method as we mentioned for the non-commuting graph of dihedral group of order 8, we can find the same relations between the number of edges and the probability, this is the coprime degree, the number of edges, and the sum of all entries of the adjacency matrix, the sum of all entries of adjacency matrix, and the coprime degree, the number of edges of non-commuting of coprime graph, and the summation of all entries on the diagonal of Laplacian matrix, and the sum of all diagonals, entries on the diagonals of the Laplacian matrix, and the coprime degree. So there are 2 examples of a group graph related to a group, the probability of a group, and the matrices. We just give a relation between adjacency matrix and Laplacian matrix. You can follow the same thing, the same method for other probability and graphs related to groups, which I have already mentioned in the first and the second part of my lecture. Now, let me state some research project. I defined the insiders matrix, but I haven't used for these 2 examples. So the first question is that, can we find a relation between probability, number of edges, with the rank of incidence matrix? We have mentioned, we have already mentioned the rank for the incidence matrix. So what we can say about the relation between the energy of graph and probability? If we have an energy of a graph. So is that possible to find the exact amount of a probability, or conversely, right? And finally, if we have two groups, G1 and G2, such that their associated graphs are isomorphic. So if we denote the graph associated to the group G1 and G2 by gamma G1 and gamma G2, so if we have isomorphism between two graphs, so can we say the probability of G1 and G2 are the same? It means they have the same probability. Or do we have the same energy for these two groups? The same question for the Laplacian energy. So we have many questions and many research problems concerning the probability graph associated to a group and matrices. I just mentioned 4 matrices, but we have some more matrices, right? So in the 3 parts of my lecture, I just give some ideas about some relations between group, probability, graph, and matrix, right? So I hope that you can just get some ideas about defining some more probabilities, some more graphs related to groups, and other kind of matrices. Okay, so let me stop this part and put some times for your questions and comments. Thank you very much for your attention, and let me thank again Prof. Budji, Prof. Intan, and other colleagues in ITB for inviting me to give this series of lectures on group, probability, graph, and matrices. Thank you very much indeed.
Okay, so let us give an applause again for our marvelous speaker. Okay, that's the last part, the last session of Professor Erfanian's lecture, matrices, graphs, probability, and groups. So is there any question for this last session? Okay, from Univ Pertamina, Rangga Nugraha.
Yes, is it okay if I speak?
Yes, of course.
Dokter, Assalamualaikum warahmatullah.
Assalamualaikum.
Waalaikumsalam. Doctor, can I see your last slide, Doctor? Your last notes? I'm really interested in the third part, I think.
Problem. Okay. Ganchila, could you put the last part?
Okay. Wait a second.
Oh, the last one is that if we have isomorphism between two graphs, right? So
Yes,
consider two groups, and we have isomorphism between two graphs. So the problem is that if we have isomorphism between two graphs, so what property of the first graph can be transferred to the another graph. For example, if we have energy for the first graph and we also have energy for the second graph, so do we have the same energy? Or what we can say about the eigenvalues, about anything? You know, that's a series of questions about the just transferring properties of the first graph or first group. We can talk about the first group to the another one through the isomorphism between two graphs, because we know the isomorphism between two groups is more stronger than the isomorphism between two graphs. If we have two isomorphism groups, so we may have many properties coming from the first to the second. If the first group is abelian, so the second one is abelian, they have the same order. We have many things. But in graph, the situation is a little bit different, because in graph, isomorphism between two graphs means that we should have a bijection between two vertex sets, and they should preserve edges. That's the only thing. So preserving edge can be guaranteed to give us more properties from the first graph to the second graph. That was my question, and that was the sets of questions you can do for just some sort of these graphs.
So I think I have a comment about this question, Doctor.
Yes,
when we have two isomorphic graph, it means that when we see the Laplacian matrix or the adjacency matrix, it is actually we exchange or we swap to rows, and then we swap to columns. In that sense, the Laplacian matrix of those isomorphic graph will be similar. And we know that if we have two similar matrices, we will have the same exact eigenvalues. So the Laplacian energy will be the same. Also, it will work if we work. It will happens if we work with the adjacency matrix. It comes from the similarity of the matrix, Doctor. What do you think, Doctor? Is it?
Yes,
probably?
I think so. But if you see the Laplacian matrix, we have two kinds of Laplacian matrix. The Laplacian matrix, which I mentioned, is the vertex Laplacian matrix. We also have edge Laplacian matrix. So we have the same question for the edge Laplacian matrix, which is more complicated. It's not like the Laplacian matrix. But you are right. So in this case, we may have, of course, we may have two isomorphism graphs. If we have two isomorphism graphs, so certainly, of course, we may have some with different rows or columns. It doesn't matter. So we'll get a similar things. Yes, it is true. But the point is that, can we say about the other properties in between groups, right? So what we can say about the properties of groups from the first group to the second one?
For that one, it is a hard question, Doctor. I also don't know what to do actually, but thank you for the comments, Doctor.
All right, thanks.
Okay, thank you to Rangga and also to Professor Erfanian. And then we have the second question from Jericho Gormantara from ITB. Okay, Jericho, would you like to ask the question directly to Professor Erfanian by unmuting your microphone, maybe? Okay.
What's the question?
Okay, I will read the question. Dear Professor, we know that in the Laplacian matrix, its diagonal entries represent the degrees of each vertices, and by that, we have trace of Laplacian matrix is the sum of all degrees, which is all we know is equal to twice the number of edges. My question, What about the anti-diagonal entries? I mean the lower left corner to the upper right corner. Is there anything we can say about that? Or maybe the sum of the anti-diagonal entries? I'm very grateful if you know something about these anti things. Thank you.
Well, it's a very interesting questions. And I suggest that you can follow this solution for this, because the situation is a little bit different. You know, since we know that the sum of the degrees of all vertices is the twice of the number of edges, that was the reason that I consider the diagonal of Laplacian matrix. But if we consider the anti-case, maybe it's a little bit different, but I'm sure that we can be able to find another relation between this matrix and the number of ages. I think it's possible. We have to think about that.
Okay, thank you so much. And then for the other question, is there any question? Okay, so that's the end for the last session. Again, let us give a big applause for our marvelous speaker.
Thank you.
That's a great talk, Professor
I was supposed
Erfanian.
to have many questions, so I just finished earlier for because in the second part of my lecture there was no time for questions, so I just put that time for this section. So if there is any more questions, so I'm available here. So
Yeah,
you may ask. Don't worry about the time.
yeah. Is there any question maybe?
Okay, just let me say a few points. If you are interested to, because I introduce several probabilities and graphs related to groups and some matrices. So if you are interested, because you know, for each of them we can do some research project and we can have some joint work. So any of you who are interested to do something on this area, you can keep in touch to me. So my WhatsApp number and my email is on the just first page of my slides, and you can just contact me for having some more joint research. I will be very happy to have some joint work with some of you who are interested in this area. Okay, so let me thank again all participants for it's a long talk. It was about 6 hours from the morning until the afternoon. So I'm sure that you are so tired. And I'm really thank the ITB Institute for having this opportunity. And if you are interested to have the same subject, not only for group, but also for ring, for module, and semi-rings. So we may have the same series of lectures, just focus on rings, modules, vector space, and some other algebraic structure. So hopefully in the future, we can be able to have the same things. And there are many research projects related to just algebraic graphs related to algebraic structures, because the ring is very important. Of course, group is important, but the ring is also very important. So we may have the same situation for some other algebraic structures. So thank you very much all of you for putting your time today from the morning until this afternoon, and hope that the situation of coronavirus change. I hope that the coronavirus disappear and we are able to see all together in a workshop in ITB Institute or maybe some other university like 2 or 3 years ago, which I was in ITB and UGM. I had some workshop that times. So I hope that the situation comes better and better and we are able to meet all together. Thank you very much, all of you. Thank you very much for Puji. Thank you very much, Prof. Intan, Prof. Editary, the Dean of the faculty, and all of committee of this algebra seminar. Thank you very much indeed.
Yeah, thank you so much. Okay, let us give a big applause again for Professor Erfanian. Yeah, actually, I have read a book that said knowledge grows exponentially. The more we know about something, the greater our ability to learn, and the faster we can solve many problems in our life. So, to appreciate the great knowledge that was shared by Professor Ahmad Erfanian, we have a virtual gift that will be given by the head of Algebra Research Group, Professor Puji Astuti. So, to Professor Puji, the time is yours then.
Okay, yeah. We would like to give some memento. Kantina, yeah.
Siap, Bu.
It is about caricature, about
It's
to remind you.
interesting.
Saya harus apa nih Kantina?
Tinggal diserahkan saja, Bu.
Nggak tahu.
Suara saya terdengar, Bu?
Ya, menyerahkannya gimana nggak tahu saya.
Oh. Jadi ini karya salah satu mahasiswa kita, Bu.
Oke. Bentar. Aku harus gimana? Ya, Prof. Erfanian, this is what's painting by one of our student.
What's the student's name?
Kantina, probably you know what's your student name? The painter.
The name is Bimo, I think.
Ya, Sultan Bimo Rizko, Bu. His name is Sultan Bimo.
Cukup ya?
Iya.
Aku nggak tahu.
Okay.
Menyerahkannya nggak tahu.
Yeah.
Aku nggak tahu menyerahkannya gimana.
Yeah, so that's this caricature for Professor Ahmad Erfanian, and we will send it after this lecture, after this day one of algebra seminar. Then.
Thank you very much.
Okay. Yeah, thank you very much again for Professor Ahmad Erfanian and also Professor Puji Astuti. Let us give big applause for all of us then. Okay, and then before we end today's event, we would like to invite every participant to turn your camera on for the afternoon photo session. And also, please don't forget to use the virtual background we have provided. Okay. Okay, operator, are you ready to take the picture?
Yes.
Okay.
Okay, great. We will take the photo 3 times since there are 3 slides here. So let's prepare our big smile. Okay, 1, 2, 3. Great. Again. 1, 2, and 3. Cheers. Okay, for the last time. 1, 2, and 3. Yeah, that's perfect. Great. Thank you so much, everyone. Yeah, we have arrived at the end of day 1 of the algebra seminar. To all participants, please don't forget to fill a Google form to record your attendance in this afternoon session. I think the link has been shared in the chat box by our committee. And yeah, we would like to deliver a big thanks to our today's lecturer, Professor Ahmad Erfanian, and of course, to all participants. And like what Professor Puji said in her welcoming speech, that even though this event is only held virtually due to all the COVID-19 restrictions, but we hope it doesn't reduce the benefits of this program to all participants, especially to broaden your mind in algebra. So we hope that you all enjoy all of the sessions delivered today and gain new knowledge. So I am Fitri. Stay safe, everyone. Good afternoon, and see you for tomorrow's session. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam.
Thank you, Fitri.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you, Fitri. Thank you, Prof. Erfanian. Prof. Ahmad,
Thank you, Gantini.
Thank you, Prof.
Thank you for your efforts. For
My
just,
pleasure.
I hope that my slide was not so bad. The quality, I know the quality, it was not very good, but I to try to send, because if we have a lecture, just not a recorded lecture here, sometimes we may have some problems, connecting problems, so we may just disturb the seminar. So that was the reason that I prefer to record my lectures. Okay, thank you very much.
Thank you.
Indeed.
Thank you very
for
much
your
for the
efforts.
It's a big
recording.
effort for you, Professor Erfanian.
Thank you.
And the recording is very good for us because it's slower. Yeah,
Yeah.
I think it's slower, so it's help us to understand. Yeah.
So thank you very much indeed. Have a nice time in Indonesia. Have a good time. So goodbye,
See you.
everybody. Okay. Assalamu alaikum.
Waalaikumsalam.
Mohon izin.
Ya.
Aku izin ya.
Ya, Ibu. Terima kasih, Bu.
Terima kasih, Bu.
Ini
Terima kasih banyak ya semuanya.